Good morning, everybody. Can everybody take a seat when they get a chance, please? We're going to get started here. I wanted to thank everybody for coming today. It's been a kind of a long journey for us for quite a few months of planning this event. So thank you for coming to our PFAS seminar. We're calling it PFAS in California, Past, Present, and Future. Essentially, the State Water Board is hosting a 2-day technical seminar, and we also have a concurrent Datathon that's going to be happening starting later this afternoon after lunch. And so it's revolved around just technical information that has to do with PFAS, both what we currently kind of know and kind of history, nomenclature, and then what our current landscape, and then kind of what the futuristic ideas out there are for either the remediation or treatment of PFAS. So that's the objective today. We have a great panel of scientists here today and tomorrow. So we encourage you to come up and introduce yourself when there's an opportunity that arises. So let's go over a few announcements if we could, please. So we need to go over emergency procedures. So if there's any alarm system that goes off in the building, we are all have to exit calmly out the Byron Share, please. And then we'll head out down to the first floor lobby and out to Cesar Chavez Park. So I'm sorry, it might be raining, but it is the park that's across the way from the EPA building. Restrooms are out the 2 doors and to the left, both the men's and the women's restrooms are out there. There are handouts in the back for the biographies and the abstracts for all of our speakers today. And we also provided a little local restaurant eatery list. So at lunch, you have some places to go that are close and within walking distance from here. I wanted to let you know that there are water board staff and other that have name tags. If you have any questions, please feel free to grab one of those folks, and we can try to provide answer your questions as we can. So we are webcasting currently right now. And I know there are folks right now looking online, so thank you, everybody out there that's also watching us. So the webcast link is available up on the screen, but you can also go to the State Water Board calendar, and they're all listed there. So you just click on the link there. If you have any online questions, those on the webcast, there should be an email provided there for you to send, and we have folks that are manning that station in the room. And after the event, this recording and the biographies and abstracts will be available on the Water Board's PFAS website for your enjoyment at a later date, if you'd like. Let's go over the format of the panel presentations. So over the 2 days, we have 5 panels. We'll have 3 presentations per panel. This morning, we'll have the first panel, and we'll break for lunch, and then we'll have 2 subsequent panels after that. For each panel, we're going to have a designated moderator, and we're going to be rotating around with water board staff. It's going to read their bios and kind of an introduction to those that are going to be speaking today. We plan on each presentation to be about 20 minutes in length. And then it should give about, hopefully, 10 minutes for presentation. So we'll run each presentation back to back to back within the panel, and then we'll have questions at the end. So this is the agenda for today. So after my introduction, I'll be handing it off to Board Chair Esquivel. Then the State Water Board will provide an update on their actions. And then we'll start with panel number 1. We'll break for lunch. And then we'll continue with panels 2 and 3 for the afternoon. And everything is out on the lobby on the posters as well. And then if anybody needs another agenda, I can get more copies made. So our concurrent Datathon is going to start at 1 o'clock. That is going to be happening in a separate room. So if anybody is interested in joining the Datathon, Scott Coffin will be organizing that, and there'll be posters to direct you in that way. And we have 3 themes that are listed up there. And so we have data scientists is going to be leading those Datathons. So Scott's going to give a complete introduction at the start of that Datathon to explain everything that has to do with that. And just quickly for day 2, we'll start again up here at 9 o'clock. We'll have 2 panels in the morning. We'll break for lunch. And then what's kind of going to be neat is that those folks that are in the Datathon, they're going to do a short presentation of kind of the work that they're working on, that they've been doing since this afternoon and then tomorrow morning. About 5 to 7 slides. It could be kind of the concept that they've been working on, kind of a product that they've been working on, an app or whatever, and they'll come in here and then we'll give them the ability to kind of present to everybody about what they're doing and maybe some of the stuff that they still need to be doing. So, and then we'll close it out at the end of tomorrow. And that's just a quick thing about the Datathon for tomorrow. So with that, I'll hand it over to Board Chairman Esquivel.
Thank you so much, Wendy. I really appreciate, I know all the time and work and effort that it took over the last really months to put together these panels and these full two days of discussion. So good morning, everyone. My name is Joaquin Esquivel. I'm chair of the State Water Board. I have the pleasure of leading the board at certainly a very interesting time on a number of fronts, this being one of them. And I think the attendance today and the interest, I think, on the webcast reflects that. Quick overview of the State Water Board. The State Water Resources Control Board has regulatory purview over water quality regulation in the state of California, drinking water regulation, and water rights administration. And the drinking water component is just 5 years on since the Division of Drinking Water was transferred from the Department of Public Health over to the State Water Board. I bring that up because in the context of PFAS and its all sub-constituents and chemicals, is a new occurrence insofar as the State Board having not only its water quality regulatory authorities and its investigative authorities on the landscape and trying to find out the sources of PFAS, their fate, where they've gone to, where they're still actively being perhaps dispersed onto the landscape, but then also how that translates onto the drinking water side for us, how that translates into regulations that then protect public health as we consume drinking water that is then pulled from those sources in the natural environment. And so it is certainly an interesting time, but I think the interest as well from the public is sometimes tinged with a good amount of uncertainty and fear. And I think that comes from not only this contaminant of emerging concern, but other contaminants of emerging concern that are also on the State Water Board's sort of radar. And I think it's important to make sure we put into proper context our efforts around this contaminant of emerging concern, how it falls in with other known contaminants, ones that we have what are known as maximum contaminant limits on the drinking water side. But for these that we don't yet have those, as we develop them, as we learn, as we gather and synthesize the technical expertise, not unlike we're doing in these next 2 days collectively here, it's important to, again, kind of couch that uncertainty and not let that sort of drive a sort of a fear of your drinking water systems, or a sense that there's this overwhelming, and are these overwhelming challenges out there. PFAS can seem like an overwhelming challenge. It's certainly long-lived constituent, its bioaccumulative properties, the fact that it is really ubiquitous in our everyday lives. But I don't think that should let us grow overreactionary. I think that there is a time and space here that we at the State Board are acknowledging insofar as we develop a maximum contaminant limit, as we start to weigh the pros and cons and synthesize again that best available science and data to guide, what should we set limits at? And then at the same time also, where are we seeing hotspots? Where are we seeing places where contamination has happened? Who are responsible parties for that contamination? All of these aspects are things that we at the State Water Board are very mindful of as we approach this very challenging constituent. So I just really appreciate everyone's time and attention today. I appreciate certainly our panelists who are lending their expertise to us as we, again, learn as much from them and from you all in your engagement as we continue to really try to address PFAS in a way that is comprehensive, is mindful of all the other things that are out there as well. We at the State Water Board with the Safe and Affordable Fund now are in the middle of really driving and developing a program that gets that million Californians that are not accessing clean and safe, affordable water now with known contaminants that we have maximum contaminant limits for, like arsenic and nitrates. And so, we do try to properly couch all of this work in that ongoing space, and are just incredibly appreciative of all, again, the expertise, leadership, and from everyone, from the public onto our water districts, and again, the scientific and academic communities that are here and will be sharing thoughts today. So just thank you all, and I'll let the State Board staff inform you a little more deeply about all the ongoing efforts that we have on the water quality side, insofar as our investigative orders at airports, chrome platers now as well, places where we know PFAS has been used and could potentially be a source of then discharge into the environment, and a thing that we need to be aware of. But again, I'll let staff do that a little more deeply, and again, just appreciate everyone's time and attention today. So thank you.
Okay, is it on now? Good morning, everyone. My name is Shahla Farnok. I'm Assistant Deputy Director with our Division of Water Quality, and I'll be doing a joint presentation with my colleague Dan Newton, Assistant Deputy Director with our Division of Drinking Water. Together, we're going to be covering what we've been doing on source and public water system investigation, share with you some of the data, talk about our efforts in getting data and collaboration and working with the military, the Department of Defense, as well as what are some of the upcoming actions for 2020. Thanks again for taking the time in this weather to come and be here in person. We appreciate it, and thank our panel members as well that they have driven today long distances. So this is just kind of a timeline. The national attention to PFAS started during 2013, 2015, when US EPA, under their unregulated contaminant monitoring rule, there was a directive to conduct testing across the nation, and that indicated PFAS and PFOA as compounds that were being detected in different locations. EPA came in with lifetime health advisories of 70 parts per trillion in May of 2016, and the State Water Board in June of 2018 identified notification levels and response levels for PFOA and PFOS, which were the two compounds at that time that were most of the focus was 14 parts per trillion for PFOA and 13 parts per trillion for PFOS. EPA issued their action plan for PFAS February of 2019. Some of you were here last year during our March workshop where we talk about our upcoming efforts for 2019 and beyond with respect to source investigation, drinking water system investigations, and working across with our industries to get an understanding of what's happening in California and where we have detections. We identified a phased approach at the time, but throughout the time, as we have learned more, we have modified that phased approach. And later on, Dan is going to talk about AB 756, which is a recent legislation, talk about the notification levels, so I won't cover those here. And then we also just sent orders recently, October, the last set of orders we sent. So I'll be talking about those. As you know, we're starting this, there would be more background later on, but landfills, because they receive municipal solid waste, and airports, because of training and fire response sites, were the primary areas where we thought we should start our source investigation, as well as look at the water supply around those areas to see if there was any potential impact to drinking water sources. These orders went under Water Code Authority and required testing for groundwater, soil, and leachate samples to be taken. The way these work is the recipients of the orders were required to submit a work plan to our regional boards. Our regional boards review those plans, and once approved, they do the investigation. So starting in January, we expect to have data coming in from these source investigations gradually over time. At the same time, we identified the public water systems that within the proximities of these facilities, as well as some of the UCMR3 rule where the detections were targeted as for additional testing. The first quarter of data for those facilities have already been in, and Dan is going to share with you where you can get that data and the results. And this one, for the source investigations, we asked for a one-time testing. For the water supply testing, it's a quarterly testing for 4 quarters. The second quarter data, as I believe, is in, but is being QC'd and should be available, but we'll wait for that. This is just a visual of how far we reached out for UCMR3 detections. Division of Drinking Water identified wells that were within a mile of those previous detections to do additional testing. For landfills, we went out a 1 mile radius, and for the airports, within 2 mile radius. We also recently sent orders to chrome plating facilities. When we talked in March, we mentioned that we will be looking at primary facilities, but fortunately in California, to the extent we know, we don't have any manufacturing facility that actually makes those compounds, but we have secondary industries that have used those as part of their process. Chrome plating facilities use those to protect their workers from chromium-6 fumes. So we sent those orders just recently on October. The facilities have an opportunity to let us know if our records are incorrect and submit a questionnaire. The work plans are due by end of March. And it's the same thing. The proposed work plans include influent, effluent, stormwater, soil, and groundwater sampling, and they're supposed to submit sampling and analysis. We send these orders to 271 facilities. We identified this through our collaborative efforts working with Department of Toxic Substances Control and Air Resources Board. Oops, I think I skipped a slide. So this is just a visual. We are kind of constantly looking at the statewide level, what are the areas that we have been targeting as these orders go. As you see, there are some areas that there's huge concentration, especially when we send orders for chrome plating facilities. Seems that there's a lot of them in 2 specific regions in California, but it actually shows how we have a statewide representation of the data, and it would lead to how Later on, we're going to use this information to adaptively manage the data we're getting, looking at the water supply testing, looking at the source investigation, and then kind of doing maybe some watershed-based analysis and not necessarily continue doing all these statewide orders. The information gathered from these facilities is also a good representation for our Office of Environmental Health Hazard Assessment to get data that may feed in later into public health goals and eventually MCLs. It would also inform us as we start looking at domestic wells that are not currently under the purview of the Division of Drinking Water. Department of Defense, as most of you know, they have been very active for years testing the water supply wells within their facilities or outside their facilities that provide water to the occupants of these bases. So they have had that data. They also have been active in coming up with the test methods. If you notice in previous slides, for the media other than drinking water, we're using their certified method to do the testing. So we have been talking to them. We have some of their data. We're working on getting their data electronically. We understand that the data was kind of limited using a different test method, but it's important for us to have that. We also working with them on the facilities they had identification to have into source investigation to use that data to decide actions. DoD is also very active in doing testing on treatment technologies. Just for your information, the State Water Board for years, since 2000, we have had what we call our groundwater ambient monitoring assessment program. This program was initiated per legislation. It was kicked off with some funding from prop funds, and we basically under that program with a contract with United States Geological Survey, USGS, we do a trend analysis and a baseline analysis of the groundwater quality in California. So recently we have an annual contract we updated. USGS added the 24 PFAS compounds to their analysis, and also as part of our future contracts, this would actually be required for them to do it. They do their work in study units. They have completed some of the study units. So they release data as they have it, but they also go back to each study unit every 5 years and do a trend analysis. So we think this information is going to be very valuable because it's really not biased. It's not looking at the places where we find it. It would enable us to understand maybe there are places or industries or things that we didn't think it would be there that is detected. So it's a good background data for us. And I think with that, I'm going to turn it over to Dan Newton to cover the rest of the presentation.
Thank you, Shala. As she mentioned, I'm Dan Newton with our Division of Drinking Water. Starting with this slide, we have roughly 14 labs that are credited per method 537.1. The transition from 537 revision 1.1, as you can see, we have 3 labs, is occurring over time. As the revision 1.1 certification comes due, we only offer 537.1. So it'll be a matter of 2 years at most that all labs will be testing for PFAS in drinking water using analytical method 537.1. We also have 10 labs that are accredited for QSM version 5.1. The lab capacity was a very critical component in how we moved forward and selected labs, or pardon me, selected wells for testing of PFAS. That seemed to be a critical path, and I just want to emphasize that. As lab capacity increases and we learn more, we'll be able to reach out a little broader. So recent legislation that was mentioned in the timeline, Assembly Bill 756, was passed in July of 2019. That, in essence, does 2 primary things. It increases our authority to a more of a general order authority. That's something new for DDW in the past, and the orders that were received for PFAS testing recently, we used the Public Health and Safety Code, and those were discrete orders to discrete wells for the unique testing of PFAS. With this new legislation, we're able to do more of a broad brush approach select groups or regions of wells as necessary using a single order. Secondly, it increases reporting requirements. Those are quite robust. The intent of AB 756 is to really notify and keep the public informed. Traditionally, our notification levels and response levels, when they're exceeded, it's a recommendation to notify the public. With AB 756, when a response level is exceeded, it is a requirement to either take that well offline or notify the public through quite a robust outreach program. We're working on details on that to share and an FAQ as we move forward, and currently that is under review within the division, but we should have that out soon. So on this slide is a matrix with the two constituents, PFOS and PFOA, identifying our analytical methods, the health effects, and over to the right you'll see our advisory levels. We had interim notification levels that we issued in 2018 that were 14 and 13, and we just updated those this year to 5.1 and 6.5, so those notification levels lowered. Our response level still sits at the current level of 70 combined for both PFOS and PFOA, and that matches right now the federal health advisory level. Recently, we released the first quarter results. Those are on our website, linked here in the second box, the gray box, the waterboards.ca.gov, /PFAS. On that website, we have a lot of FAQs, but we also post our results. The first quarter of well testing is provided via an interactive map. We have several maps that focus on PFOS and PFOA, and then drill down into all of the analytes. The maps get more sophisticated, and there's a lot more ability to slice and dice the data as you wish. The raw data is also available on an Excel spreadsheet for your use. Here's a snapshot of the first map. This is the most basic version of the map, and I find the most helpful. This map is a demonstration of wells that exceeded the response level and exceeded the notification levels. For instance, the blue here, bar graph at the bottom left, those are the wells that were below the notification level. We had 369 wells that tested below the notification level. The yellow is above notification level, but below response level, and we have 178. And to the right, we have two levels of concentrations that exceed the response level. That's 70 parts per trillion. We had 11 wells between 70 parts per trillion and 100 parts per trillion, and 12 wells that were over 100 parts per trillion. So in total, we had 23 wells that exceeded the response level out of the roughly 600 that were requested to test. On the map to the left, you can see those circles with coloring that identifies the exceedance of response level, notification level, or not. The next slide is a bit of a focus area, areas of interest. To the left, we've got some wells that were in excess of the response level in the Bay Area. Down in the Santa Ana area, we have more of a broad level of detective PFAS. You'll also notice in that same Santa Ana area up in the right, Corona, we have quite a few wells that exceeded response level. It's interesting to note that those wells, we checked on those wells that exceeded response level. Most wells have been taken offline or treat because of PFAS or treat because of other things, but are likely effective on PFAS. So the response has been very proactive and interesting. Those wells that are still online are typically non-community water systems, very small water systems at places of employment, for instance. Another graph that we share on our web is, and this is just one of many, is the frequency of constituents based on our sampling. As you can see, PFOS and PFOA are in the top three. We've got some other analytes that are quite common in California. We believe the top 7 of those analytes has quite a bit of health data, and we are contemplating or considering looking at notification levels for those analytes, but that is currently under review. I just want to share that PFOS and PFOA currently have NLs and RLs, but there may be other notification levels coming based on review of what's prevalent in the state and what we have health data for. So this is a timeline looking forward. It starts with the passage of AB 756. Prior to that, or around that time frame, we asked OEHA, the Office of Environmental Health and Hazard Assessment, to consider setting a public health goal for PFOS and PFOA. So that started this process, and that's what this timeline looks at. You'll notice in the green bubbles is roughly a 1.5-year timeline for OEHA to provide a public health goal. From that process, another 1.5 years after that, starting in the summer of 2022, roughly, the Water Board will go through its public process in establishing an MCL. That process takes about 1.5 years, and as you can see on the far right of the timeline, the last bubble, it's possible we could have an MCL in the fall of 2023 for both PFOS and PFOA. And so with that, I'll turn the slideshow back over to Charlotte to finish up.
Thank you, Dan. So just wanted to give you a heads up on what are we looking at for 2020, just in case you're wondering when are my constituencies going to get an order. This is what we are looking for ahead for the upcoming year, as well as the fact that we have always been reaching out to industry representatives, trying to coordinate our effort through them. So there shouldn't be any surprises. As we learn from our data, as I mentioned earlier and Dan mentioned, we'll be looking at potentially going beyond the radiuses that we had identified outwards to do additional testing of the public water systems, look at the watershed-based approaches. We've done statewide orders to target facilities that are primary areas where we expect PFAS was used. But moving forward, there would be our regional boards working with our team to look at the data from public water systems, looking at the source investigations, and looking at the areas to potentially identify how we can actually protect our water supplies from potential migration of these compounds to the water supply system. So that would be our primary goal. We have been talking to the industry, they're talking about sampling of wastewater treatment facilities. We'll be looking at influent, effluent, and biosolids, and anything that comes in and goes out of the facility. We're going to be looking at sending orders to require testing, source investigations at refineries and bulk terminals. Those are the two that we're probably going to go out early in next year. As I mentioned earlier, we are getting data from DOD. We expect to integrate that data into our data so we can have a better visual representation of what's going on in the state, as well as requiring additional sampling of water systems that are outside those bases. So we're working with our Division of Drinking Water to identify the list. Domestic well is definitely in our mind, to our GAMA program. We do some domestic well testing, so we may have some data, but we're looking at the strategies, options, at least in the hot spots, in the areas where we have detections, to go out and offer testing and work with the domestic well owners to get their wells tested to make sure that they are drinking safe water. Data analysis and visualization is going to be a challenge. We've started with some. We're going to kind of look at existing systems and figure out how we can evolve them to better synthesize the data, kind of link the data from source investigations to public water systems, also have a transparent system that an average person can go in and find out what's happening in their area. And that's part of the reason we're holding this technical seminar, to actually learn. As our chair mentioned at the beginning, this is evolving, this is an emerging compound, so we're trying to learn and adapt to it as much as we can during this uncertain time. I have some resources for you where you can get additional information. There's a listserv you can subscribe. All the data and work plans and information will be publicly available on our website. All the data that's submitted to the drinking water system is also pulled into our GAMA and synthesized to show it in a different way, as well as the ways that Dan mentioned, for those of you who want to do your own data analysis and dig in. With that, that concludes our presentation, and I appreciate you starting the morning with us.
We're going to take just a short few-minute break. We're going to move everybody down. We anticipated a full house, so we anticipated to put everybody up. So we're going to do a little bit of rearranging. So got 5 minutes. How about that? All right.
Good morning. We're going to go ahead and get started in about 1 to 2 minutes. So if everyone wants to get their seats. I have the mic. Good morning. We're going to get started in about a minute. Great. My name is Annalisa Kihara with the Division of Water Quality at the State Water Board, and I'll be moderator for our first panel that will be covering the PFAS history, use, nomenclature, chemistry, and toxicology. So our first presenter is Erica Calv. She is a professional geologist at the San Francisco Bay Regional Water Quality Control Board. Erica will be setting the stage for today by providing a background on PFAS. Ms. Calv has nearly 20 years of experience in the environmental field, overseeing site investigation and remediation of soil, soil gas, and groundwater. She also spent several years serving as the Emerging Contaminants Focus Group leader and team coordinator for an international PFAS team at Arcadis. As part of that experience, she had the opportunity to edit an Emerging Contaminants Handbook for practitioners and co-authored the chapter on PFAS. Ms. Calv recently joined the San Francisco Bay Regional Water Quality Control Board and provides regulatory oversight of several cases, including 2 airport sites that are responding to the PFAS investigative orders mentioned by Shala Farnak. In addition, Ms. Calv is a key member of the Water Board PFAS team implementing the statewide PFAS source investigations. So her presentation will be followed by Ms. Taryn McKnight, Product Manager for Eurofins Test America, based in Sacramento, who will cover PFAS chemistry and fingerprinting. Ms. Knight has 20 years of experience in the environmental testing industry. She is the company's subject matter expert on PFAS and vapor intrusion. Ms. McKnight has extensive experience with a wide variety of complex regulatory programs, such as the Department of Defense, vapor intrusion, and emerging contaminants. In her current role, she is responsible for providing technical guidance and support to clients, agencies, and industry personnel across the country. So the final panel presentation is a joint one by representatives of the Office of Environmental Health Hazard Assessment, also known as OEHA, covering the current knowledge on the toxicological effects from PFAS in humans. So this presentation will begin with Dr. Melanie Marty, who is Assistant Deputy Director for the Science Programs at OEHA. Dr. Marty has been with OEHA for more than 30 years and previously served in other acting Deputy Director and Assistant Deputy Director roles with the agency. Her work has largely been in risk assessment of environmental contaminants, including developing guidance to adequately address susceptible subpopulations such as children. Dr. Marty has served on a number of US EPA peer-reviewed committees, including the Science Advisory Board committees, and was the chair of the US EPA's Children's Health Protection Advisory Committee from 2001 to 2009. Dr. Marty received her PhD from the University of California, Davis in pharmacology and toxicology. Dr. Marty will be followed by Dr. Chris Banks, a staff toxicologist at OEHA and who has been developing public health goals in the water toxicology section since 2011. Dr. Banks received his bachelor's degree in biochemistry from the University of California, Los Angeles, and his PhD in environmental toxicology from the University of California, Riverside. And now we'll begin with the first panel presentation by Ms. Erica Calv.
Thank you so much, Annalisa, and it's really a pleasure to be here today to give this introduction to PFAS presentation to you all. Really briefly, we'll just go over the outline. We're going to talk about what are PFAS, including the nomenclature, manufacturing processes, and uses. And then we're going to talk about why we care, and mainly that it's present in our drinking water supplies. It's known to cause some health concerns, and over time we have an increase in our awareness. So what are PFAS? Just kind of quickly, PFAS represent a very broad class of more than 6,300 organofluorine compounds according to US EPA's database on PFAS. They've been used in a wide range of industrial and commercial applications since the 1940s. And the reason that they're used in so many products is because they impart a really unique surface active properties to oil and water repellency, temperature resistance, and friction reduction. They can be categorized into long and short chain PFAS. The long chain PFAS are known to be bioaccumulative, toxic, and very persistent in the environment. Short chain PFAS are known to be toxic and persistent as well, but they're less bioaccumulative and they are, but they're more mobile, so they're still of concern. PFAS and PFOA are the most well-documented in literature. They're long-chain PFAS. They can also be referred to as C8 compounds. And PFAS are, in general, are non-reactive, stable, persistent, and bioaccumulative. PFAS can be broken into families and classes. So this is just a really simple diagram showing naming convention to kind of get some nomenclature together. So they're broken into two families, polymeric PFAS and non-polymeric PFAS. And in general, in the environmental field, we are talking about the non-polymeric PFAS because those are the ones that we're detecting ubiquitously in the environment and are more mobile. The polymeric PFAS are bound, in plastics and, may present a future risk for environmental concern. Within the non-polymeric family, there are two major classes that are that we can kind of break this class of 6,000 compounds down into, and that includes the perfluoroalkyl acids and the polyfluorinated compounds, which are also referred to as PFAA precursors because they biotransform in the environment and they break down to these final degradation products, which are the PFAAs. So the next two slides are kind of go into those two classes in a little more detail. So first off are the PFAAs. These are the compounds that are most commonly used in a standard, or reported in a standard analytical method. So the PFAAs have at least 6 groups of PFOS that can be discussed. And primarily when it comes to the environmental literature and research that's been done, we've looked a lot at the perfluorosulfonates and the perfluorocarboxylates. The perfluorosulfonates, or the PFSAs, are kind of the poster child for that class is PFOS, and it could simply be referred to as a C8 sulfonate. So if you kind of want to make sure people understand you, when you could talk about PFOS or PFAS, those two acronyms sound really similar. So you could just simply say it's a C8 sulfonate, and people will start to understand what you're talking about. Similarly for PFCA, PFOA is the poster child, and it is a C8 carboxylate. And then we also have these perfluoroether acids that are coming onto the scene. In particular, perfluorocarboxylic acids, PFECA or PFECAs, are kind of recently introduced to the marketplace, I think, in the last 10 to 15 years. And the poster child for PFECAs would be Genex and Adona, and they are the replacement compounds for PFOA as a processing aid for making PTFE, or kind of commonly known as Teflon for using a brand name. And so when you go to the store and you're buying a nonstick pan and it says it's PFOA free, what that means is they didn't use PFOA to polymerize the nonstick coating on the pan. They used Genex or Adona or some other PFOS compound. So, and then there's also the PFAS, they're the sulfonic acids, and F53B is an example of that, and it's used in chrome plating instead of PFOS. So the naming convention can seem daunting at first, but most of us in this room are familiar with the hydrocarbon naming convention, and there's a lot of similarities between the naming convention for PFCAs and the naming convention for PFSAs. So most of us know that when I talk about methane, it has 1 carbon and 4 hydrogens. When I'm talking about octane, I'm talking about a compound that has 8 carbons and a hydrogen attached to, or several hydrogens attached to it. So in the world of PFOS, PFOS, it's octane sulfonate. It has 8 fully fluorinated carbons on its tail. So let's see. So if you're looking at this this drawing here, this portion is referred to as the tail. It's fully fluorinated and it has 8 carbons on it. And then it has this functional group on it. It's a sulfonate, and that's commonly referred to as the head of the molecule. And kind of similarly, you have perfluorooctanoate, or PFOA, which has the O in it, and it also indicates that it has 8 carbons. But those 8 carbons include 7 fully fluorinated compounds and 1 carbon on the carboxylate head. But regardless, it's a C8 compound. And that's just important because when you go out and you research this, you want to know what people have been calling it. They call it a C8 compound, and there's a whole C8 panel who's helped kind of come up with a decisive list of health effects that are now agreed upon in the court of law. So it's meaningful to know that that's what those are. So within the group of polyfluorinated classes, there are, we often, as you become familiar with the chemistry, you start to understand that the manufacturing process makes a really unique set of PFAS. And so there are several types of manufacturing processes, but the primary ones that have been used to date are electrochemical fluorination and fluorotelomerization. And some common electrochemical fluorination products include these perfluorosulfonamidos. And so this is just a short list of classes that can be derived using an ECF manufacturing process. And the interesting thing about those compounds that are shown here, these sulfonamidos, they biotransform in the environment to form PFSAs. So those are the dead-end daughter products. So those are the ones we can analyze for. So it's really interesting when you understand, where these are being used, such as, as a surface treatment on carpets. Then you might know, okay, well, over time, that's going to biotransform into a dead-end daughter product like PFOS. And then for fluorotelomers, this is just a very short list of fluorotelomer classes that can be produced. And then fluorotelomers break down and biotransform in the environment to form PFCAs, and those are dead-end daughter products. So just a historical perspective on PFAS manufacturing. Kind of, as I mentioned, there's two dominant manufacturing processes that we're aware of. ECF processing was the dominant manufacturing process all the way up until the early 2000s when it was voluntarily discontinued by the major manufacturing company at the time. And then at that point, it transitioned over to being fluorotelomerization as the dominant process. And then more recently, like these Gen X and Adona compounds, those are made using a process called oligomerization. And then kind of just high level, it's just interesting to see that, these products have been in use since the 1940s, and they found their way into a number of consumer products. And as early as 1978, some manufacturers became aware of PFAS in the blood of their workers, but for whatever reason, it took almost 30 years before that information became, to the forefront, such that we now have a PFOA product stewardship program that the US EPA has developed, and these compounds, PFOA specifically, and related compounds have been phased out as part of that as of 2015. So, as I mentioned, there's a wide range of historical PFAS uses, and the way that we're talking about it in terms of ongoing future use is what's essential and what's not essential. And ideally, we focus on using these for essential products. There are some products that they're really useful for. We use them in our technology, to manufacture circuit boards and semiconductors, and there's several other uses that may be very appropriate, but we just have to manage them properly. And then there's a lot of things that they don't need to be in, like I don't want it in my food packaging. I don't want it to touch my food, and I don't want to actually be consuming it because my food was packaged in PFAS-containing paper that was wrapped around my burger. Or interestingly, FDA has a poster out there where they tested several products out in the marketplace, and it was found in chocolate cake at a concentration that literally, if I saw it in the environment, I would think, if it was an environmental sample, that it was pretty close to a source area. So it's kind of scary and something worth, kind of starting to ask, like, what's in my consumer goods? What's in my food? What's in my water? So why do we care? You guys saw this earlier. We know that it's been detected in California's public water supply. We have a high frequency of detection of these compounds. We saw this chart earlier today that and this one's just grouped by class. So we have 302 wells with sulfonates present. We have 241 wells that are impacted by carboxylates, and then I think there's like a slight misnomer here, but it's 6 wells have Adona in them, not a FOSA. But so, shoot, I apologize because this is actually a draft of my presentation deck, so I'm kind of adjusting a little bit, which is why there's a highlight here. I'm going to skip this slide and that slide. So kind of the important thing that, we want to realize about PFAS is even though they're detected ubiquitously in the environment, and several people, when they're asked to sample for it, they might complain that but it's present at background levels, above your health advisory level. And that's true, but its source areas are significantly higher concentration than what we see in background levels in the environment. So primary and secondary manufacturing facilities are commonly known major sources of PFAS. Class B firefighting and training and response areas are, metal plating, landfills, and wastewater treatment plants. So we can start by looking at these hot spots and doing something about it. And, you know, kind of a traditional approach with other contaminants is you bite the head off the snake, you treat the source area, you get rid of the hottest stuff, and then, yeah, there might be some other material that's left that needs to attenuate over time, but, you know, that's at least us getting started on a solution. So as I mentioned, you know, they are detected ubiquitously in the environment, PFOS in particular. It's interesting to look at this distribution of screening criteria for different types of water bodies. We have this range of drinking water criteria here that's obtained from various government, you know, state and federal and I think other countries. Consumption of fish, like a surface water criteria for consumption of fish by fishermen, aquatic toxicity surface water criteria, and a consumption of aquatic organisms by bird criteria. And since we're focused on drinking water here right now, just kind of a reminder, so this is where the health advisory level sits, and it's kind of highlighted by a pink dot. This is California's notification level, 6.5 nanograms per liter, so that gives you kind of a sense for the range here. The method detection limits, they range from, you know, around 1 nanogram per liter up to around 10 or 11 nanograms per liter. The drinking water samples can certainly be measured at the lower levels, and then the more complicated and the environmental matrix might be, it'll increase the detection limits. And then, as I mentioned, they can be detected at ambient levels and as high as the health advisory level. So that's a concern, but doesn't have to prevent us from moving forward with identifying hotspots. So just as a kind of, just to put this in perspective, as I mentioned earlier, there's about 10, you know, at least 6,000 or more compounds in this class. So if this box represents, this outer box represents 10,000 PFOS, the inner box, this gray area, is what we've actually been able to catalog by CAS number. And then this little box here, which represents around 25 compounds, or, you know, anywhere from 18 to 24, is how many we can actually see using standard laboratory analyses. And that's just kind of an interesting perspective, since it's clear that we know very little about the entire class. There is growing awareness, so this is kind of meant to just highlight, you know, where we started back in 2000, where we understood a little bit about PFAS and PFOA being present, to, you know, kind of more currently, where we're aware of all these compounds, the Gen X and Adona. We have all of our fluorotelmer compounds listed, not all of them, but some listed. And then where we're going, we're aware that there are some ultra short compounds like this TFMS. This is like a methyl sulfonate or a C1 sulfonate compound, maybe volatile. There are polyfluorinated cyclic sulfonic acids that are detected ubiquitously in the environment as well, and those are not being kind of assessed at this point. So it's just kind of good to know that, you know, there's a lot more out there for us to learn. We have several precedent-setting cases that have come. So in 2012, the C8 panel was formed, and that helped us to identify that PFOA exposure is linked to 6 diseases, including kidney cancer, testicular cancer, ulcerative colitis, thyroid disease, pregnancy-induced hypertension, and high cholesterol. In 2017, DuPont settled with Ohio Man for $12.5 million in damages. And then there's a huge class action suit that was just settled recently. And then 3M settled recently with North Alabama Water Authority, and there are several other ongoing class action suits. And with that, I guess that's the end of this presentation.
Okay, and we're going to hold questions until the end of the panel presentations, and we'll be loading up the next presentation. Is it on here?
Okay, thanks everyone. Erica did a great job of giving an introduction to the chemistry. Now I have the honor of diving a little deeper and talking about what makes that unique chemistry such a challenge from an analytical perspective and a data usability perspective. I am missing the clicker. You have it? Okay, so she mentioned that there's, that acronym PFAS stands for per and poly, the completely fluorinated and the incompletely fluorinated chemicals. And what makes that uniquely challenging is we haven't identified very many of those incompletely fluorinated chemicals. There are believed to be hundreds of them, and they have the potential to biotransform in the environment. So these unknown chemicals out there that can eventually become those known chemicals that predominantly make up our target analyte list that we consider our risk drivers today. And those are those alkyl acids, the PFAAs. And so what you see here on the top, you've got the perfluorinated chemical. It means each one of those carbons in that carbon backbone is completely fluorinated. The hydrogen's been replaced with a fluorine. So it has that very strong, persistent bond that's not known to degrade in the environment. Now, the incompletely fluorinated chemical you see below it, the poly, that has some hydrogen still attached, a weaker bond, susceptible to a certain amount of breakdown and transformation. Now, it's important to understand that this transformation can only go in one direction. So fluorinated chemistry takes an enormous amount of energy. It's not occurring naturally in the environment. So those hydrogens are not becoming fluorinated. That portion of the molecule is being cleaved off. And what you're left with then is the shorter, completely fluorinated portion of the molecule. Now, Erica mentioned some of those different manufacturing processes, and one of those processes, the ECF, resulted in the occurrence of branched and linear isomers. So branched and linear isomer is a same chemical, same formula, same atoms, just a different arrangement of those atoms, like what you see here for PFOS. Now, the significance of this is laboratories have to have standard reference material in order to quantify something in your sample. We have standards for the linear version of the chemicals that we report. We have very few branch standards. They don't exist. So that means as an industry, we are potentially underrepresenting the true mass of PFAS in the environment without capturing those branched isomers. Now that head and tail that Erica was talking about, this leads to these surfactant properties that these chemicals are so widely used for. You can think of it like a duck in water. So they have a head that likes to be in the water and a tail that likes to be out of the water. So the tail is that carbon backbone and the head is the functional group. And those competing tendencies make these chemicals very surface active, which leads to challenges in terms of collecting and identifying, analyzing, and reporting these chemicals accurately. So why are PFAS such a unique analytical challenge? And we've touched on a few of these so far. So they've got some of those unique properties that make them very surface active. You can think of them like sticky compounds. They're believed to be ubiquitous, so you're going to have problems with background sources. They exist in a range of concentrations, yet we're all chasing these ultra trace level limits that are applied to pristine drinking water. And maybe the biggest challenge facing us right now is the lack of a consensus best analytical method. So the EPA has published a drinking water method, EPA 537. It is for finished drinking water only. There is no other EPA method for any of the other matrices. So what do we do when we need to test for groundwater, wastewater, landfill leachate, any other matrix beyond drinking water? The answer to that question is pretty confusing. Right now, it's most likely that you're getting a modified 537 analysis. But all that means is it's a user-defined method. That means the laboratory that's supporting that sat down with their own knowledge and experience, wrote an SOP, standard operating procedure, and that's how your data is generated. And that means it can vary from one lab to another. Also, there's a particular point of contention with the EPA about calling a drinking water method modified, since they don't lend themselves to modification. But we had to call it something. So that's where we sit right now with the modified nomenclature, but then there's all these other method references out there adding to the confusion. So you have this ISO 25101 method. It's only acknowledged in the state of New York, and that's probably because it's not very useful. It's so generic and not prescriptive that by the time you finish modifying it to make it useful, what you have is a 537 modified. And also, it only applies to PFOA and PFOS, which, as an industry, we have moved far past just looking at those two compounds. Now, the EPA Region 5 Chicago lab published these two ASTM methods, 7979 and 7968, for the non-potable water and solid matrices, but they were never multi-lab validated, and they represent some antiquated technology, so they were never widely adopted by the commercial lab community. Then the EPA got to work on drafting some methods that would go through that multi-lab validation to address those other matrices. The first one they came up with was EPA 8327. This method is still draft. It was released for public comment this summer. That public comment period has closed, and we are awaiting a final published method. The method itself has been characterized as a rapid screening tool. It is based off of the ASTM method, and again, not expected to be widely adopted or utilized by the commercial lab community. Then they got to work on another method. So this will be an isotope dilution method, and I'll talk more in a minute about the significance of that, but it's basically the method we've all been waiting for. They're working on it in conjunction with the Department of Defense, so it will meet the Department of Defense needs for testing PFAS. And right now it's slated to be published as a 1600 series method. We don't have the method number reference yet, so it's 1600 something. Now there's drinking water method 537 that was recently updated to 537.1. Then the EPA got to work on a second drinking water method, 533. So that method just went through third-party validation, and we are waiting for them to finalize it and release it for public comment. And there's a bit of confusion about the role that this method will play. So it represents some similar qualities to the 537 method and some dissimilar. So there's some overlap in analyte lists, some different analytes, some different analytical techniques, and so it's not really clear how these methods are supposed to be used and applied. Will you always have to use both of them? Will you have to use your professional judgment to determine which one is appropriate? And if so, how would you make that determination when typically we have no idea what compounds we expect to be present at a site until we start testing? So hopefully they'll find a solution and recommendations on how to move forward with those methods. Now, the reason I have DoD QSM listed up here is to make a clarification. A lot of people will refer to the DoD method. DoD does not publish methods. What they do publish is something called the QSM. It's a quality systems manual. It's just a collection of quality assurance criteria to ensure that they're getting consistent data across program laboratories and that it's very robust and defensible data. Now, what the DoD typically does is they take an EPA reference method, let's say 8260 for VOAs, and they'll say, okay, you're gonna follow this method, and then you're also gonna do this, 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 and this to make sure it's very rigorous data. They didn't have that option with PFAS for groundwater and soil and all those other matrices. So they had to put so much criteria into the QSM that it reads a little bit like a method, and that's where we get that confusion from. But it's also what a lot of folks at state and commercial industrial level have been turning to as a stopgap measure. When there is no EPA method, how do they have confidence in the data that they're getting? Well, let's apply the DoD QSM criteria, which is exactly what the state of California did. Oh, and just for your reference, there is no method reference. Their method reference is PFAS by LCMSMS compliant with table B15 QSM 5.1 or latest version. And right now they're up to version 5.3. So let's take a deeper look at those future EPA methods. So we have that draft 8327. We're waiting on the final version of it. There's that future isotope dilution 1600 series method, and then that additional drinking water method. And here's how they kind of compare. So they represent either a solid phase extraction preparatory step, that's the SPE, or just a simple direct inject onto the instrument with bypassing that prep step. As far as the quantitation scheme goes, that draft 8327 is an external standard. That's part of that antiquated technology I was referring to. The 1600 is isotope dilution, which is considered the gold standard of quantitation. And then the 533, they're talking about utilizing isotope dilution, but potentially allowing for internal standard quantitation. So one of those things that's yet to be seen what they'll land on. And then what they're applicable for, the 8327 is strictly for the non-potable water. The isotope dilution 1600 will be for non-potable water and solid matrices. That's one of the great benefits of isotope dilution is you can capture everything with it. And then the 533, they're also uniquely talking about it potentially being applied to not just potable water, but maybe non-potable water as well. So we'll have to see. So until that time that we have that coveted EPA isotope dilution method, we have to find ways of managing and reducing variability in data sets. And these are some of those key elements we have to be mindful of, aware of, and monitoring to make sure that we are reducing that variability. And these are the things that the Department of Defense took on and have addressed in the QSM. But it starts with how the samples are prepped, and then that quantitation scheme that's used, and then understanding the experience of the laboratory to be able to employ these pretty sophisticated techniques. So let's dive a little bit deeper into a few of those. Branched and linear isomers. So I mentioned they exist in the environment and we're maybe underestimating them. But for those that the branch standard exists, here's a picture of what it looks like. So on your left column there, you've got PFOS. The standard is on the top and the actual sample is on the bottom. So you can see in the standard, those two peaks, you have the branch peak and the linear peak. Down below in the sample, same thing, the branch peak and the linear peak. Looks great, we quantify both. In PFOA, we don't have the branch standard. So you see the linear standard there on the top, and then down in the sample, you see the linear peak, but then right next to it, you see the branch peak. But because we don't have a standard for it, it doesn't get quantitated. So it's not part of the total that's reported. So that's how we're underrepresenting the true mass of PFAS. And then there's this emerging question in our industry right now about what data we can use for a forensics application. And so there's this movement to utilize branched versus linear data. So you look at those ratios of percentage of branch versus linear, that can give you some indication about sources, the type of manufacturing that was used to produce that product. And it's not that this can't be used, but it's important for everybody to understand what they're actually getting with this data. So branched and linear separation is not as black and white as it sounds. There are unresolved branch peaks in the linear peak. So it's not just truly the linear that you're getting. You're getting unresolved branch that's part of that. And then for the branched peaks, we only have standards that incorporate some of them. So for example, PFOS, don't quote me on this, but I think the branch standard includes maybe 12 of the branched, but they've identified like 89 branched. So you're getting some idea of the branch, you're getting some idea of the linear, but it's not an exact science at this point. A really important element in in the analytical process that we employ is, with the LC-MS technology, is monitoring for the secondary ion transition. So if any of you are familiar with a SIM analysis like they do for PAHs, selective ion monitoring, it's a similar concept. And we have the option to just monitor for the primary, or we could also monitor for the secondary. So this is something the DoD states, you have to monitor for the secondary. And here's an example how this can impact your data. So again, on your left, you've got the primary ion transition. You look at the standard there on the top and the sample there on the bottom. Everything matches up nicely. That looks like PFOS at a certain concentration, it gets reported. But if you look over to your right, you have the secondary ion transition that we're monitoring. Look at the response in the sample versus the standard on top. It doesn't match, right? So that tells us that there's something else going on here. So we would, at best, report that as a qualified result. So wouldn't you like to know that PFAS was maybe not above the 70 part per trillion health advisory limit in your sample, and that it was really qualified maybe due to matrix interference or something else? So isotope dilution is really the cornerstone of the analytical techniques that we employ for PFAS. And there are numerous benefits to this. It's considered the gold standard because it's the most accurate form of quantitation. What we do with isotope dilution is we take labeled, isotopically labeled compounds and add them to your sample at known concentrations before we ever do anything to the sample, before it's prepped or analyzed. So if we have PFOS, we take a labeled PFOS, add it, and we monitor to see what happens to it throughout the process. If we know that we got 40% recovery of the labeled PFOS, we know we got 40% recovery of the actual native PFOS that was in your sample, and then we can recovery correct for that. That's enormously important and beneficial with these challenging chemicals and in the matrices and at the concentrations that we're dealing with. And here's an example of how this kind of plays out in a data set. So on the top there in box A, we have PFOA. If you look at the isotope dilution result, it was 10 parts per trillion. And if you look at the matrix spike and matrix spike duplicate, which is for the purpose of measuring what kind of matrix impacts there may have been in the sample, you see that we had about 80–90% recovery. It's pretty good. Now, if we did just an internal standard analysis on that, we would have reported 9 parts per trillion. With the isotope dilution, we get to recovery correct for that little bit of matrix interference, and we would report 11 parts per trillion. 9, 11, pretty good, but there wasn't a lot of matrix impacts in that sample. So now look at the box below in slide B. So for the compound MeFOSA, we had an isotope dilution result of 40 parts per trillion. Now look at the matrix spike. We had 50% recovery, so quite a bit more matrix impact in that sample. Now if we use the internal standard approach, we would have reported 40 parts per trillion. But with isotope dilution and recovery correction, we get 80 parts per trillion. Pretty significant impact there on the data set. And now that isotope dilution approach becomes all that more critical when we start trying to apply these techniques to complex matrices. So let's talk landfill leachate, which was one of the first sources that California targeted in their investigations as primary sources. Now, matrix impact, landfill leachate is the definition of matrix interference. So you've got, a wide range of concentrations of not just target compounds, but non-target compounds, a whole slurry of stuff, and we're still trying to chase those very ultra-low detection limits. So with isotope dilution, we get closer to achieving that goal than with any other analytical technique. And then the same goes for air, another complex matrix that's getting more and more attention right now, looking at the emissions from manufacturing facilities. These are known to adsorb to particulates, and they do have short and long-range transport properties, so this is a concern. There's a number of DoD facilities that are doing research on PFAS and source air because when you think about the treatment for PFAS, it all comes down to incineration or thermal type of oxidation, and so all of those facilities have a stack where whatever's treated is going out into the ambient air. And so we have to be able to measure and ensure that we are getting absolute destruction, that we're not just causing these to transform into other PFAS chemicals. And so we have to be able to address that complex matrix as well. And so we need those sophisticated analytical tools to get there. And then my last chemistry topic for you is just an analytical technique that kind of starts to peel back the layers on that concern about precursors. So those polys, the incompletely fluorinated chemicals that can biotransform in the environment. Like I said, we haven't identified many of them, but we know they're out there. So what do we do about it? If we haven't identified them and we can't test for them, how do we have any idea what's at our site? Well, there was a procedure developed called the total oxidizable precursor, TOP assay. It's a pre-treatment step that's done in the laboratory. It is not meant to be representative of natural conditions in the environment. It is intentionally an artificial, forced transformation of those precursors to those dead-end products that we're concerned about. And so it gives you this directional measurement. We force the oxidation, we force the conversion of them, and we get an idea of the total mass of those oxidizable precursors that could be sitting at our site. And so an example of what this looks like in a data set is here in this table. We took a precursor compound called PFOA. We spiked 500 parts per trillion of it into a sample, ran it through that pre-treatment step, analyze it again for our target analyte list that represents our risk drivers. And what we see is the PFOA is gone. It's non-detect, it fully converted. And what it converted into was predominantly about 70 parts per trillion of PFOA and a smattering of some of those other perfluoroalkyl acids. So this gives you an idea. Sometimes it can be used as an initial investigative tool when you're trying to characterize your site. You might use it alternatively at the end of your site investigation and remediation when you want to close out a site and make sure there's nothing else residual there. But it falls short of being an answer to the question, what's the total PFAS at my site? And it's very clear that everyone understands that because people want the answer to that question very badly. Academics are working on that, but we don't have a commercially available analysis to answer that question at the moment. So this gets you a little bit bigger of that picture, like Erica showed, that tiny little box of all the PFAS. Well, it spreads that box a little bit further, but it doesn't get us quite all the way there. The primary value of the TOP assay is it tells you that subset of unknowns that are there that can turn into the risk drivers that you are testing for. That's why you'd want that information. So that's it. Needless to say, we have a few challenges ahead of us still, but the good news is, technically speaking, analytically speaking, we have developed robust techniques for generating defensible data. Many years ago, they're available. We just need the EPA to document them and publish them in a method. Okay, thanks.
Thank you, Taryn. We're going to take a minute to make sure that we have the next presentation loaded and it's the right version. So there's a few minutes for those of you in the back who are standing up. We have plenty of seats up front if you want to snag a seat. For those of you that are jotting down questions for the panel, hopefully you're jotting it down in these cool notepads that we have in the back. If not, feel free to grab one on your way out. And I just wanted to make a reminder for those of you that are tuning in via the webcast, we have a team member here manning our email. So please feel free to email any questions that you have to auditorium@calepa.ca.gov. Again, questions at auditorium@calepa.ca.gov, and we'll start in 1 minute.
I got theirs right.
Okay, while we're loading up the presentation, just wanted to share that we do have more bios, and I think it's just the bios or agendas? Bios? Probably both. Bios printed, and they're at the back. Okay. Okay, I think we're all set. Presentation coming on. Okay, so I'd like to introduce Dr. Marty to start the presentation for OEHA.
There we go. It's better. So mostly today, actually Dr. Banks is going to give the presentation, but I did want to start by introducing who OEHA is, because a lot of people don't know what we do. We're kind of a small organization within Cal EPA, but it stands for the Office of Environmental Health Hazard Assessment, and we are dedicated to promoting a healthy California environment. We are primarily toxicologists, epidemiologists, some physicians, and some other environmental health scientists. And our major responsibility really is assessing the potential health risks of environmental chemical exposure. So we are working on PFAS through a number of programs, and especially our water program. With that, I'm going to hand it over to Dr. Banks, who is our staff lead for the water program on the PFAS.
All right, thank you for being here today. We've had some really good talks about the background of PFAS, so I'm not going to spend a lot of time talking about the background. And this talk is going to focus predominantly on the toxicology of basically PFOA and PFOS. Those are the two chemicals that I'm going to focus on because from a toxicological standpoint, those ones are the best studied. Okay, so there are many health concerns with PFAS, and their kind of unique chemistry sort of makes them a unique challenge to study from a toxicological standpoint. Firstly, they are extraordinarily persistent in the environment. So those carbon-fluorine bonds are really strong and they tend to stick around. And because of this persistence, there is widespread occurrence in many different types of environmental media, including water, air, soil, and food. And as mentioned before, many PFAS do bioaccumulate as well, which means that they're readily absorbed, but they're not easily eliminated. And once these chemicals are absorbed into the body, they can lead to, or they are associated with many different health effects, including liver toxicity, immunotoxicity, developmental toxicity, cancer, and endocrine disruption. PFAS can also cross through the placenta and get into breast milk, so developing fetuses and nursing infants can be exposed to PFAS chemicals as well. And I do want to mention that both PFOS and PFOA were listed under California's Proposition 65 as developmental toxicants back in November of 2017. So when it comes to exposure of Californians to PFAS, the bottom line is that practically everybody is exposed to PFAS to some degree. And we know this because of the work that California's biomonitoring program does. They do a lot of work tracking or measuring PFAS levels in blood and in different populations. And it's, in 94 to 100% of samples that they've looked at, PFAS has been detected, some of the common ones like PFOA and PFOS. Some of the other PFAS substances have been detected less frequently, but there's still often a very substantial number of detects. And biomonitoring work is continuing to go on. There is this California Regional Exposure Study, or shortened for CARE, that is evaluating PFAS concentrations in people in 8 regions of California. And right now they're looking at 12 different PFAS, but they want to expand that level to 30. And I believe that the results from the CARE LA study from the Los Angeles region are up on the biomonitoring website, which you can go take a look at if you're interested. The biomonitoring data is really important for several reasons. One is that it helps us characterize exposure to PFAS across Californians. So it kind of tells us which PFAS chemicals we are actually being exposed to and gives us an idea of how much. It also helps us understand the various sources of PFAS and identify how we're being exposed to PFAS. Where is the PFAS coming from? And it's also very important to evaluate how concentrations can change over time and whether any interventions that may be put in place to reduce or minimize PFAS exposures are effective. So PFOS and PFOA are no longer manufactured in the United States, and the NHANES survey, the National Health and Nutrition Examination Survey, reports that PFOA and PFOS levels are going down in the general population over time. So it seems like this phase out has been effective. So to really get a handle on the toxicity of PFOA and PFOS, we're looking at both animal toxicity studies and human epidemiology studies. And I'm going to start by talking a little bit about the human epidemiology data. So human epidemiology studies have been conducted in many different populations, including high exposure workers, in high exposure communities, and in the general population as well. And many adverse health outcomes have been associated with PFOS and PFOA exposure. For example, high cholesterol and elevations in liver enzymes in the serum, which is indicative of liver damage, has been associated with exposure to PFOA and PFOS or PFOS in all types of populations. For carcinogenicity, IARC, or the International Agency for Research on Cancer, did an assessment on PFOA in 2018, and they concluded that there is limited evidence for humans for the carcinogenicity of PFOA. And a positive association was observed for cancers of the testes and the kidneys. And newer studies are constantly coming out. I was recently made aware of an Italian study that looked at PFOA exposure in workers, and this study found a very strong association between liver cancer and PFOA exposure. And there's also additional support for other toxicity endpoints, such as thyroid disease in women and children, chronic kidney disease, developmental toxicity such as low birth weight and being small for gestational age, which is an indicator of reduced fetal growth, and reproductive toxicity as well. A lot of work has been done to characterize the relationship between immunotoxicity and exposure to PFOA and PFOS. And in 2016, the National Toxicology Program released their systematic review that they did on immunotoxicity in PFOA and PFOS. And they concluded that both PFOA and PFOS are presumed to be an immune hazard to humans based on a high level of evidence from animal studies and a moderate level of evidence from humans, from studies in humans. And the evidence that these chemicals affect multiple aspects of the immune system supports the overall conclusion that both PFOA and PFOS alter immune function in humans. So it's safe to say that there are definite adverse endpoints from PFOA and PFOS exposure in humans. Okay, looking at the animal toxicity studies, for PFOA and PFOS, there's actually quite a large database of animal toxicity studies, and these chemicals are relatively well studied. For some of the other long-chain PFAS, it's kind of a mixed bag. Some chemicals do have toxicity studies, other chemicals have no toxicity studies. And so this poses a challenge for us when we're trying to think about the totality of PFAS. But for PFOA and PFOS in any case, and some of the other ones that we've looked at, we do tend to see very similar toxicity endpoints. We see a lot of liver toxicity. The liver seems to be a major target organ for these chemicals. We also see toxicity of the reproductive system, the immune system, and the thyroid. Those are sort of the major toxicity endpoints that we see, effects in those systems. But we also do see reports that report endpoints in the neurological systems, kidney and heart, and impacts on lipid homeostasis and metabolism. And I do want to point out that these long-chain PFASs do tend to have very long half-lives in humans. And this is an important consideration when doing risk assessments on these chemicals, and I'm going to talk a little bit more about this on the next slide. For the short-chain chemicals, the animal data is somewhat limited, but there are toxicity studies out there for various chemicals. And in fact, the US EPA does have draft assessments out for 2 of these short-chain chemicals, PFBS, which is the perfluorobutane sulfonic acid, the C4, and GenX, the hexafluoropropylene oxide dimer. These chemicals, we do see similar toxicity endpoints. We see reproductive toxicity, immunotoxicity, and kidney toxicity from these chemicals. And there is suggestive evidence that GenX is carcinogenic as well. So going back to the issue of half-lives, when doing these assessments, we really need to pay close attention to the half-lives of these chemicals and other pharmacokinetic considerations. One, because there are large differences across animal species. So if you look at the column for PFOA, in rats and mice, the half-life is ranges on the order from hours to days up to weeks. But in humans, the half-life ranges from 2 to 5 years. So if we want to use animal studies as the basis for a human health risk assessment, this needs to be accounted for, this major difference in half-life. And we see a similar trend for PFOS as well. There are also large differences across different PFAS chemicals. And I have here the perfluorohexane sulfonic acid and perfluorohexanoic acid as an illustrative example of this. So PFHXS is a C6. It is very similar in structure to PFOS, except that it is 2 carbons shorter. And PFHXA, the hexanoic acid, is also C6. It's very similar to PFOA, except that it is 2 carbons shorter as well. And if you look at the human half-lives of these 2 compounds, for the hexane sulfonic acid, the half-life is from 5 to 8 years. But for the hexanoic acid, the half-life is 32 days. So there's a really big difference in the way this chemical is interacting with the body. And we need to be aware of these sort of considerations when doing our assessments. Additionally, there are even sex differences between animals in the same species, and females tend to more rapidly eliminate PFAS than males do. So these are all things that we need to think about when using animal studies as the basis for the human health risk assessments. So earlier this year, OEHA gave their notification level recommendations to the Water Board, and OEHA developed reference levels, both non-cancer and cancer reference levels for PFOA and PFOS. For the non-cancer reference levels, we derived values of 2 parts per trillion for PFOA based on liver toxicity in female mice, and 7 parts per trillion for PFOS based on immunotoxicity in mice. For the cancer endpoints, we derived values of 0.1 parts per trillion for PFOA based on liver and pancreatic tumors in male rats, and 0.4 parts per trillion for PFOS based on liver tumors in rats. So in our recommendations, OEHA stated that the notification levels should be set at the lowest levels that can be reliably detected in drinking water using currently available and appropriate technologies. And this is because the reference levels that we derive tend to be below reliable levels of detection. And so the Water Board did so, and they set the levels at 5.1 parts per trillion for PFOA and 6.5 parts per trillion for PFOS. Since the cancer studies are really driving the numbers here, I wanted to spend a little more time and talk about the actual cancer data that was used to derive these numbers. So for PFOA, we evaluated these 4 studies here, and 3 of these studies are long-term 2-year bioassays in rats. So the Butenhoff study, the Beagle study, and the NTP study. In the Butenhoff et al. Study, so male rats that were exposed to PFOA for 2 years had a significantly increased incidence in testicular tumors. In the Beagle study, male rats exposed to PFOA had increases in liver tumors, pancreatic tumors, and testicular tumors. I do want to point out that this study only had a control group and one dose group, so we weren't able to do any sort of dose response analysis with this study. In the Filgo et al. Study, pregnant mice were administered PFOA, and then the pups were then followed for 18 months to see if there was an increased incidence in tumors. And those pups did have an elevated incidence of liver tumors. And most recently, the NTP, the National Toxicology Program, released their 2-year bioassay data at the end of last year, and they showed that exposure to PFOA induced increases in liver and pancreatic tumors. And it's the NTP data which really drove our assessment for PFOA. So here are the actual tumor data, and if you look at the column on the far right for pancreatic tumors, you can see that at the lowest dose of 1 milligram per kilogram per day administered over 2 years, you see a really big increase in the number of pancreatic tumors, jumping from 3 out of 43 up to 29 out of 49 animals. And we see increases at both the mid and high dose as well. For the liver tumors, at the mid dose, we're seeing significant increases in liver tumors as well, and also at the high dose. So these data were peer-reviewed by the pathology working group, and a lot of work was done to ensure that these results are accurate. And since this is a rat study, and we're using this as the basis for human health reference levels, we wanted to make sure that those major differences in half-lives was accounted for. And so what we did is that we used plasma concentration as the dose metric of choice. So instead of using the administered dose. So the plasma concentration, the amount present in the blood, is what we use as our primary dose metric when extrapolating from the animal studies to the human studies. Okay, going to PFOS, there was really only one publication that looked at carcinogenicity of PFOS, and that's this Butenhoff et al. 2012 study, which is a publication of an older 3M study that was done in 2002. So in this study, rats, male and female rats, were given PFOS in the diet for 2 years, and hepatocellular liver tumors were seen in both males and females. And there was also a significant trend for pancreatic islet cell carcinomas in male rats. And these data were the basis for the reference level of 0.4 parts per trillion for PFOS. So I'm not going to go into any of the specifics of how the numbers were calculated, but if anyone is interested in how we did derive those numbers, that information is available in the technical support document, which can be found on OEHA's website. So OEHA did consider PFOS for carcinogenicity. It was evaluated as a carcinogen because of the positive animal carcinogenicity study from Butenhoff, the assay from Butenhoff et al., and because of the similarities in chemical structure and biologic activity between PFOS and PFOA. So both chemicals are pretty similar in many ways. Structurally, they are similar in that they're both linear 8-carbon perfluorinated molecules, and importantly, their biological activity is also quite similar. So in the studies that we looked at, in terms of the non-cancer endpoints, we were seeing the same types of toxicities pop up. So there was a lot of liver toxicity, a lot of immunotoxicity, reproductive toxicity, and thyroid toxicity. And based on this, we believe that that treating PFOS, or that evaluating PFOS as a carcinogen, is supported by the data. So recently, the Water Board has asked us to develop public health goals for both PFOS and PFOA, and this is what we are working on currently. So we are in the process of updating our literature search. We are planning to evaluate any new studies that have come out since we were doing work on the notification level, and these assessments will continue. And on that note, I'm going to hand the talk over to Dr. Marty, who will tell you more about what OEHA is doing.
Thanks, Chris. So Chris just mentioned we are working on the PHGs for PFOA and PFOS. And you would be amazed the number of publications that are coming out every year. There's an incredible interest in this class of chemicals. So we are, in addition to doing the PhD work, we're taking a look at other PFAS chemicals, and we're doing literature searches for those chemicals. Basically, the ones we're focusing on, we consider the exposures to humans, and it's currently based on EPA's drinking water method and the results that you saw earlier from Dan Newton. We're hoping to conduct health effects assessment using traditional toxicity testing where those data are available. And I think Dan already said that it looks like they're available for quite a few of the chemicals that we're considering now, so that's a good thing. In addition, there are quite a few PFAS chemicals for which there are no or very limited toxicity data, so we can't do our traditional risk assessment approach. For those chemicals, we're exploring grouping them and using what we call read-across methods. So you can group chemicals. We heard earlier talk about grouping them by structure. So that is one way to group them, by chemical structure. Another way is to group them by similar kinetics, which ones have long half-lives, which ones don't, where they end up in your body. And still another way really is to look at the biological activity and group chemicals according to that. And so that's something what we all have already done for PFOS in our decision to treat it as a carcinogen. In addition to the cancer data, they act very similarly to PFOA in terms of a biological sense. So once you group chemicals, then you try to look at read-across methods. And what that really just means is can you predict the toxicity of a chemical for which you don't have those animal data by looking at other chemicals that are similar. This is not a new concept. The US EPA, the FDA, and the National Toxicology Program have been working on looking at rapid ways of predicting toxicity by using not whole animals, which is very resource and time intensive, but instead cells or even cell-free systems where you just are looking at molecules that occur in our cells. So what you do is, then it's all automated, they have robotics doing this. You can test for perturbations in normal cell function, and you can gather information much faster than traditional animal toxicity testing. So for example, a carcinogenicity bioassay takes 2 years to dose the animals, takes another couple of years to do all the QA/QC, data analysis, publish the report, and you've got information on one chemical. So if you can do something better, faster, then that's what we need to do and move forward. So we're looking at these systems that are being developed at the federal and also internationally to see what we can gather about the perfluorinated compounds. So read across, what do I mean by read across? Well, what you want to do is you test known toxicants in these high throughput systems, and these are anchor chemicals, what we call anchor chemicals, with traditional animal toxicology data available and or human evidence of adverse effects. You test the PFAS chemicals that don't have animal data in the same high throughput systems, and you compare the results with the anchor chemicals. Do these PFAS chemicals perturb cells or have the same types of biological activity as the anchor chemicals? That might be used to predict the toxicity of the chemicals without the animal data. There are other read-across approaches that are being developed by academics and across the world, really, that include computer simulations. So, for example, you might know that a PFAS chemicals interact with a specific receptor in the body, let's just say for the heck of it, the thyroid receptor. So if you have a 3D structure of that thyroid receptor and you know where chemicals bind to activate it, you can then take a 3D simulation of your PFAS and see, can it actually fit into that receptor? So that's just another way of trying to get at what the potential biological activities are of these chemicals, which will take If you try to do animal testing, it's going to be 100 years from now before you get an answer. Maybe 200. My great-grandchild might be a toxicologist by then. So we as scientists are discussing all of these approaches with the federal agencies that are working on them and with federal scientists working on the PFAS chemicals in particular. And we are also discussing with academics who are developing these new test systems, in silico methods and other read-across methods. So hopefully we're going to be able to address additional PFAS down the line without waiting for the long-term animal studies. That is all we have to say, and I think questions will be open. Moderator?
Thank you, Dr. Banks and Dr. Marty. So we're now going to, can you hear me okay? Okay, good. We're now going to take questions for the panel. We have some roaming mics. And so please wait for a mic so those on the webcast can hear each question and each response. Yeah, I'll go that side.
I have a question for the OEA group. How do you coordinate your efforts with those of EPA, and will there be efforts to homogenize your results with those of EPA?
We have been talking with EPA routinely about what they are doing in their efforts to address PFAS chemicals. So in terms of harmonizing, we'll do what we can.
I think this question is for Erica, and it's to do that given that there are thousands, you said something like 6,300 or so PFAS compounds out there, and we typically analyze for about 20, sometimes just for PFOA and PFOS. Are you aware of any studies where the real occurrence of PFAS has been addressed, say, looking at total organic fluorine and comparing those results with just PFOS and PFOA, or the 20 that we're looking at, so that we really get an idea of, if we only have limited results, can we have some idea of what the real occurrence is?
Yeah, it's a great question. And there definitely are studies out there that are using these advanced analytical techniques. And so top assay is one that we heard about from Taryn. And it does have its limitations. So some other options that are out there are non-target analysis, which are coming online commercially. And what that does is it uses a library of PFAS compounds that right now expands, I think it's between 600 and 700 compounds are included in this PFAS library. It's been compiled by academics. And you can use this really expensive kind of Ferrari type laboratory instrument called QTOF to analyze this non-target analysis, match the spectra with what's in the library, and you can get this kind of qualitative result for what other PFAS might be present. And then, yeah, I think the AOF and EOF are two more simple and more readily available technologies, but they're just not online commercially yet. But I think that commercial laboratories are looking at that, and I personally am I'm very interested in that, and I know in the academic world, they're using it primarily to, well, I see it a lot in remediation. So when they are testing remedial technologies, they're looking at, you know, like, did I actually fully treat the PFAS in the sample? And to understand that, you can do top assay, but then you want to get a third line of evidence, that the AOF, that shows that you have fluorine mass balance, that you've accounted for it all, and that it truly went away in your final treated sample. So that's kind of like one of the gold standards for testing our remedial technologies.
My question's for OHIA. I've always been curious about the synergistic toxicology. Like, if you're looking at them just one at a time, but if they're more or less toxic around each other, different profiles of those. Do you guys have plans for any of that? Or
We have methods to address potential interactions in our risk assessment paradigms. So if we know that there's 2 or 3 PFAS that affect the liver, and we have samples from a specific site, and we were doing a site-specific analysis, we would add those risks together rather than just trying to look at them one at a time. And ditto for cancer risk, we also add cancer risk together. The key is knowing what's there.
Thanks. Quick question for the State Water Resource Control Board. We've seen the timeline for the MCL. We've seen, we've got the notification level. What about the response level?
Yes, and thank you for bringing that up. That was not in the timeline. When we did update our notification levels back in this summer, we did note that we would revisit those response levels in fall. We are currently doing that. We are actively reviewing levels in a timeline, but right now we don't have any information to share at this point.
Just a question. This is a conference focusing on water, but I'd be interested in OEH looking at food substances. And you're at, I think, 14 parts per trillion, but you're talking way down at 5 and 6 and 0.01. So are you going to change that standard, the listed Prop 65 standard at 14, and then talk a bit about food?
Let me do the easy one first, the food. Yes, we are interested in that. We're working together with our Department of Toxic Substances Control. They are right now, through their Safer Consumer Products program, looking at food packaging as a source of PFAS to us in our diet. So we are working with them and looking at the toxicity of those chemicals that they're finding and supporting their efforts to come up with alternatives for that. In terms of the Prop 65 values, those values undergo a regulatory process, so we would have to be looking at that.
A question for Erica. You had a slide on major sources of PFAS, which included wastewater treatment plants and landfills. And I guess I would note that neither of those are producers or heavy users, but rather receivers of them through residential uses. Mm-hmm. And the concentrations are exponentially less than what you would find at a contaminated site near firefighting training sites, for instance. And so that distinction always seems to get lost. And I would just note that, wastewater treatment plants nor landfill leachate are sources, but rather are receivers. And as I say, you could have 600 million parts per trillion of PFAS at a training site versus single-digit parts per trillion at a wastewater plant.
Before responding, Erica, it would be helpful for those of you to maybe introduce yourselves as well as the organizations you represent. Thank you.
Sure. Yeah, I'm Greg Kester with the California Association of Sanitation Agencies, representing the wastewater sector.
Yeah, no, absolutely. That's a really important distinction. And I think when it comes to wastewater treatment plants and landfills, it really is going to be, them acting as kind of a source, even though they're the receiver of this waste and potentially discharging, and it's just passing through their plant or through their facility. It's going to be driven by whose waste they're receiving. So if you're a wastewater treatment plant who's receiving industrial waste from, say, a chrome plater or, some other secondary user of PFAS, then you may have extremely high concentrations of PFAS in your discharge. And so when we're looking at wastewater treatment plants, what we're trying to find are hot spots. We want to kind of stop the bleeding, right? Like, let's find these places where we can make a real difference by implementing smart measures to reduce discharges to the environment.
And we're in complete agreement with that, and pre-treatment is what could be used there for industrial discharges, agreed. And just one more question for Chris. You noted the fact that blood serum levels have decreased since the phase out of PFOA and PFOS, And I would argue, that the reduction has been substantial, 70 and 84% respectively. And so it seems as if we can get the material out of commerce, that would be the most effective means of mitigating.
I agree. That would be a good way to prevent any sort of exposure if we weren't exposed to them at all. But it goes back to the essential versus non-essential uses that was discussed earlier. And if some of these are deemed essential, then there's the potential for exposure. But I agree.
So we do have some email questions that have come in. More.
So the first question is from Kelsey Hakes. She is a sales and business development engineer from Aqueous Vets. And her question is, the current response levels right now match the EPA health advisory goal of 70 parts per trillion, PFOS/PFOA. Are you looking at lowering that response level, and what and when would that be?
And this appears to be almost a repeat of the question I just answered. It's certainly something we're looking at right now. We're knee deep into those response levels and the data behind it, but we don't have any timelines or information to share at this point.
Thanks, Dan. Any other questions in the audience while we pull up another email question?
Sorry, I didn't get to introduce myself the first time. I'm Robert Kent with the USGS. This question is for Taryn, and I just want to make sure we understand what you mean by the recovery corrections when you do the isotope dilution. If I'm understanding this right, let's say you have a isotopically labeled PFOS compound, you inject it in the sample, you get back 50%. Does that mean that when you deliver my result for PFOS in the environmental sample, you double the number?
Yes, that's correct.
Thank you.
Do we have another email? Sounds good. 3.
This audience member has 3 questions. The first question is, could you please expand on the toxicity of long chain versus short chain PFAS?
Sure. The toxicity of long chain versus short chain. Well, the biggest difference between them that we know so far is this difference in half-life, and that's depends and it determines how long the chemicals are circulating in the bloodstream. We know much more about the toxicity of the long chains. So PFOA and PFOS are both long chains. Some of the other better studied chemicals are also long chains. But we do see effects from the short chains as well. So with things like PFBS, there are toxicities as well. They're just not as well studied. So this is something that OEA is working on. We are thinking about all of these different compounds. Melody, do you want to add anything to that?
Other than if you look at EPA's draft RFD for 2 of the short chain compounds, you see they're just as toxic. So maybe a little bit less here and there, but they're not non-toxic.
And the second question is, how can the consumer know that they are buying PFAS-free products rather than just PFOA, PFOS-free products?
One thing that I look for is if it says it's a high performance product, I start to question, did they add PFOS to increase the performance of the product? So, like some of the products that we're kind of learning more about is we might treat our windshields with some stuff to make water bead off of the windshield that is being found to contain PFOS. PFOS are really good at, water repellency. So kind of looking for those sorts of key indicators, and then, hopefully over time there will be, some additional rules about that'll help us understand which of the products we're purchasing contain PFOS. You could also look at the ingredients list and look for compounds that have the word fluoro in it, or if you have access to an SDS, you can search for that keyword.
Just to add to that, it kind of reflects how chemicals are used in commerce, and the fact that we really don't have a tracking system to know where they go from manufacturer to the people who use them. And so it makes it very difficult, even for agencies trying to figure out where these compounds are in what products. There is no easy way to figure that out right now.
And I'll add to that that as a laboratory, we get calls constantly right now from secondary manufacturers asking us to verify the products and the raw materials that they're getting. So they don't even know that what they're producing is PFAS-free or long-chain PFAS-free, and they're looking for verification of that because all of this is confidential business. It's proprietary. It's not hazardous substance. And so there's claims, but verification comes down to actual data. And if you say PFAS-free, you're saying 6,300 chemicals free. And as there is no analysis for that, you can't make that claim. Mostly I see PFOA-free, which you can probably assume is a true statement. Maybe PFC-free. I've seen that on some high-performance outdoor gear. That's saying it's free of the perfluorinateds, but it probably just got those replacement chemicals in it.
Last email question. Relative to landfills as sources, what materials going into landfills do you think might be the major sources of PFAS?
I think, landfills receive waste from several municipal users, and so they might receive, like our clothing may be treated with PFAS, and we throw that away. We might throw away our Teflon-coated pans, and then that's in the landfill and can break down over time. And then, landfills may actually receive industrial waste as well. So those are going to be the landfills that probably have the higher concentration. So if they're receiving some sort of, biosludge from some industrial process where PFOS is being used in large quantities, then, it would be present in that material too. And there's been a number of studies done on characterizing landfills that determined carpeting is a very significant source of PFAS in landfills, and they're dominated by the short chains, so PFBA, PFBS, the C4, 5,3, FTCA is kind of the conclusion about the characterization of landfills at this point.
Thank you. We have a question here in the front and then to the gentleman in the back after.
My name's Susan Allen. I'm with California Association of Mutual Water Companies. And I just wanted to clarify the statement that our colleague made from the wastewater treatment side of the world. I've seen some presentations where there has been an assertion that the precursors are transformed into PFAS and PFOA in the wastewater process, and that they go in below the levels of concern and they come out spiking like crazy and impacting downstream water. And so I was just wondering if that's the case or not, because it seems to me like there's some work out there that's suggesting that wastewater transforms precursors.
Yeah, so precursors can be broken down into the dead-end daughter products through primarily aerobic processes, but I think some of them do degrade in a suboxic or anaerobic environment as well. You can get kind of transformation products. And so if you or have any of those processes as part of your wastewater treatment plant, then you could have that happen. I've definitely seen a lot of publications that show kind of influent, effluent, and the conversion, or what appears to be an increase of PFAAs on the discharge side.
Good morning, Matt Small with US EPA Region 9 out of San Francisco. And my question's for Erica. Well, first of all, great presentations, wow. Erica, I'm trying to learn a little bit more about mobility of these compounds in the environment and understanding particularly fate and transport in groundwater. And you gave a great discussion of how these compounds are breaking down and reaching what you call dead-end daughter products. Can you talk about what that may do to the mobility, relative mobility within groundwater?
Yeah, definitely. There's so the perfluoroalkyl acids, the PFAAs, are present as anions when they dissociate in the environment. And those are really mobile. They may be attracted to some other, charged clay particles and whatnot, but in general, they're kind of considered to be, really high solubility and very mobile in the environment. The polyfluorinated compounds can be anionic, cationic, or even zwitteronic, which is means that it has positive and negative charges on the molecule. And the negatively charged molecules are going to be like the PFAAs and be more mobile, but the ones that have positive charges on it, those might bind more predominantly to clays, for example. And then the other thing that's kind of interesting about their mobility is that they're attracted to each other. So if you have a lot of PFOS present, then the PFOSs want to stick together and stay together. And so they also, the presence of large mass of PFOS can actually kind of present a kind of a retardation effect as well.
We do have a question back here.
Actually, I have a comment and then a question. First of all, I wanted to thank Greg for emphasizing the importance of the fact that when we're looking at landfills and wastewater treatment facilities, we're really trying to help work together as industry and us to figure out what they're getting and how we can solve the problem. We are very interested to partner with wastewater industry to understand what pre-treatment steps are, whether they're adequate, and that's why we started with chrome plating facilities, and as additional testing is being done by you voluntarily on your own or based on the orders, we hope to learn of other potential sources that we may not even know about. And it is important to emphasize that most of the time when you're looking at highly treated wastewater, that goes through processes, and we don't expect to find these products after those, high level of treatment when we use them for groundwater recharge. I think seems like, based on what we have heard, biosolids may be more of a suspect of where this stuff will end up. But I think that's something we need to learn, and that will be helpful for the landfills and other operations. I had a question, wanted to understand that there was a comment made that for PFOS and PFOA, there is Prop 65 notification requirement. So could one assume that the only reason we see like pots and pans and other products say PFOS, PFOA is because they're required to disclose that, but they're not required to disclose the other ones, even if they know it? I know we don't have anyone from DTSC, but I know Prop 65 goes with mandated notification levels.
I will attempt to answer that question. I'm not a lawyer, and our lawyer should really be answering this question, but the notification requirements under Prop 65 are really if you are doing an illegal discharge. So it's not the same. I think, though, for many manufacturers want to get out in front of any potential lawsuit, so they will put a label on their product if it contains a Prop 65 listed chemical. So you might be seeing that, but the requirement really is only if the exposure exceeds a certain level from your product. So for the product labeling. I don't know if our director is back there, if she wants to add anything to that. Yeah, I got to put our director on the spot. That's like...
Thanks, Melanie. So I'll just add a little to it. So under Prop 65, PFAS and PFOA are listed as reproductive toxicants. And so the requirement is if the level from the product exposes someone to a significant level, then warning is required. And it's a specific warning, so it wouldn't just be like PFAS are present, but it would say the chemical known to the state to cause reproductive toxicity, give the name of the chemical, is present in this product and will expose you to this chemical. So it's a little different. So I doubt the kind of labeling that was discussed actually was a Prop 65 triggered label.
Thank you. So we do have one question coming in from email.
Yes. This question is from Kate Melberg, who is an environmental engineering associate from LA Sanitation. And her question is, Is there an established method detection limit and approved testing method for measuring PFAS in biosolids?
So testing for PFAS in biosolids is the same as any of the other non-potable water matrices. It's going to fall under the user-defined 537 modified type of approach. So biosolids, wastewater, landfill leachate, all of it, soils, tissues, fish tissue, all of it falls under that umbrella. So to say an approved method might be a stretch. As far as the state of California goes, they have recognized the DoD ELAP accreditation that laboratories have for their user-defined method, and the DoD will certify you for any matrix you ask them to. So if you have that certification, you could consider it, approved under that umbrella.
I'm Rick Zimmer from Eurofins. This is a question for Dan Newton, and it relates to the notification discussion. There's really no defined detection limits required for these compounds because there's no MCLs set yet. And with the implementation of SB 756 in the coming year, I think understanding at what levels water systems should report at, since there's no defined DLR. There are NLs, but the reporting limits from the labs are much lower. And so, Dan, in the facts that will be posted by the Division of Drinking Water, will that be addressed?
Yes, Rick, thank you for bringing that up. Those absolutely will be addressed. Those items, along with how we interpret 756, the language is a little vague. We're going to provide some sample notification letters. There's also requirements as far as how to notify. That is a whole package which will include what we consider a detection.
Do you have a couple more questions? We have time for maybe 2 more.
Tiffany Thomas with NSAFE. I was curious if you've considered pulp and paper manufacturing as a primary source for your initial survey and screening, akin to the chrome platers, for example.
I don't know if they've officially made the list, but they're certainly on their radar in terms of, I'm personally aware of a big pulp and paper problem, a site in Germany where there's been, the pulp and paper creates biosolids from that process, and then those biosolids were used to grow crops, and then those crops are now contaminated. And so I think, we have a lot to do, and I think pulp and paper is one that, probably as we start to grow the list of areas of concern, that's definitely a good one.
Yeah, one thing to note on that is that we are learning from other states, and they have identified that paper manufacturers are a source. We'll take one final question.
Yeah, hello, Jason Dadicus, Orange County Water District. Questions for OEHA. What approach does OEHA take when an animal study presents a particular endpoint that when you review the human epidemiological literature, that same endpoint doesn't appear to show up? I'm thinking perhaps specifically of the pancreatic cancer endpoint that's driving the cancer reference level for PFOA.
So that's a really good question. For carcinogens, there is not an expectation of site concordance across species. What that means really is sometimes in a mouse, you'll get a liver tumor, but in a human, you'll get a tumor at a different organ. And it's even the same for across rodents. So mice and rats, oftentimes you get tumors, but in different places. So, the public health protective assumption is that the potency of the carcinogen in an animal model is going to be the basis for the potency of a carcinogen in humans. So we use the most sensitive site in that case to estimate the cancer slope factor.
Thank you. These were great questions. Please join me in thanking our panel. And I believe right now we're breaking for lunch, and we should come back at 1 o'clock. Thank you.
Adapting and go and get some more agendas and stuff. It's going to be lines are going to be long every single we should. Do we want to? There was a. Should we go over the class drive and make sure all the destinations are good? 1 p.m.
Hello, everybody. We're going to start in 5 minutes, please. 5 minutes. Two minutes, 2 more minutes. everybody. Shall we take a seat? We'd like to get this show going again. So I didn't introduce myself. I omitted that from this morning, you know, from the morning jitters. So my name is Wendy Link, and I work for the Division of Water Quality. And the other moderator this morning was Annalisa Kihara. So she also works in the Division of Water Quality. So I just wanted to put a name to the faces. I wanted maybe one thing to ask of those participating this afternoon. Is anybody interested or will be staying over to watch the movie? We are showing The Devil We Know. It is a documentary. I have to admit, it's a little harsh. So, but it is about the chemical manufacturing and the uses of PFOA and PFOS not in the state of California, over in West Virginia, over on the East Coast, but kind of the what happened in regards to that from the documentary's point of view. So how many hands were raised? Whoa, okay. One more time, please. 1, 2, 3, 4, 5, 6, 7, 8, 9. About 20 to 30 people. 20, okay. So, all right. So we'll be moving, we'll start that movie, I guess we have, it depends on where, but we've planned it for about 4:30, and it's going to be over in an adjacent room next door. So we'll move over to there when the time comes. All right, so our second panel today is titled Drinking Water, PFAS Data Analysis on Source and Treated Drinking Water and the Economic and Legal Impacts to Public Water Purveyors. We're delighted to have three folks here, Dr. Susan Glassmeyer, Dr. Matt Small, and Tim Sloan. Dr. Glassmeyer works for the US EPA. She's a research chemist and the Office of Research Development Center for Environmental Solutions and Emergency Response. Dr. Glassmeyer earned her BS from Xavier in chemistry and her MS from environmental science and Doctor of Philosophy, or PhD at Indiana University. Her research is focused on contaminants of emerging concern, both chemicals such as pharmaceuticals as well as microorganisms in the water cycle. She has coordinated several projects examining the occurrence, fate, and transport of CECs in wastewater, surface water, groundwater, and drinking water. Following Dr. Glassmeyer will be Dr. Small. Matt is works at US EPA Region 9 here locally, the Office of Research and Development, and resides in San Francisco. He works, he's one of the region's hydrology experts. He's led the effort to create the EPA OSWR, O-S-W-E-R. What does that stand for? Oswald? Okay. Thank you. Directives and ASTM standards for remediation by natural attenuation and risk-based corrective action. Matt is also an expert in contaminant fate and residual contamination transport and evaluating cleanup goals and options. Matt spent 5 years private geological consulting. He has a BS in geology from CSU Hayward. Yes, geologists. In mineral energy, a master's in mineral engineering and his doctorate in civil and environmental engineering from UC Berkeley. And following Dr. Small is Tim Sloan. Thanks for coming, Tim. Tim works for Scher Edling. He's an attorney at Scher Edling. He represents public entities in litigation directed at putting the costs of pollution on the large institutional entities responsible for it. His groundwater contamination cases focus on emerging contaminants, including PFOS, 1,4-dioxane, hexavalent chromium, and others. Tim's cases span the U.S. and address some of the most pressing water pollution issues facing public entities. So with that, I'd like Dr. Glassmeyer. Please welcome her. Thank you.
There we go. Good afternoon, and hopefully you don't get the lunchtime nap time, but I'll try to keep it up and keep the excitement going. So today I'm going to talk about a study that we've published recently looking at PFAS in drinking water systems. And so just kind of overview what we're going to talk about. We're going to look at some of the chemical concentration trends of the different compounds we looked at. Then we had 2 river systems that we had samples for, so look at some of the occurrence patterns and how PFAS is really stable in the environment. And then look at some modeling work that we did to kind of figure out what some of the sources might be in our sampling set. Look at removal during drinking water treatment, and then finally look at the relation between our data and the UCMR data that was collected after our study occurred. So as I mentioned, this is part of a larger study that we did on 247 different contaminants of emerging concern in source and treated drinking water. We collected samples at 25 different drinking water treatment plants in the source water, and then we tried to get paired residence time treated drinking water samples collected before the clear well. So we're looking at the water, same water parcel going into a drinking water plant as coming out. In addition to the chemicals, we also did one bioassay looking at estrogenicity. The map on, that is your right, is just kind of the summary of where the different locations are. We did get samples from across the U.S. The dark green outlines are the US EPA regions. We're keeping the exact sources of the different sampling points anonymous, just because this was a voluntary program. It was a single snapshot concentrations, so it's really not kind of fair to put the different locations, on blast that this is what we found. Because it was one sample, it may not be representative in any way, shape, or form of their total drinking water. It may be anomalously high or low. So just, but we did get a nationwide scale of samples. So far, we published 10 different papers out of this study, looking at, we have one paper, the overview, in 2017. Then we also delved a little deeper into QA/QC, pharmaceuticals, the bioassay, different microorganisms, and then looked at human health and ecological health of the samples, as well as the PFAS paper. So both the overview and the PFAS paper were published open access, so feel free to look at those, and if you want some of the information, some of the other papers, we can probably find a way to get you those papers as well. In terms of the methodology that we used, this is one that Scott Boone, who at the time was part of the Office of Chemical Safety and Pollution Prevention, or OCSPP, for the agency, that he developed. This is not 537, 537.1, any type of modified 537. This is a completely different method. It uses solid phase extraction, but it uses the Oasis wax cartridge instead of the C18 cartridge that's used in the 537 methods. One of the benefits of this is that he was able to get quantitative data on some of the shorter chain ones that just aren't available in the 537 methods. And also, we'll talk more about methods later on when I talk about the UCMR data. But because of the 537 was cross-lab verified, that raised the detection level that was achievable from that method. So this method that Scott developed, all of our detection limits were less than 1 nanogram per liter, and sometimes far less than 1 nanogram per liter, whereas the published 537 method, based on the cross-laboratory, is between 10 and 90 nanograms per liter. And that really kind of then pulls into the level of quantitation and the frequency of detection that we saw in this project compared to the UCMR, just because we had much, much lower detection level. So for those of you that like methods and that type of thing, this is a little bit of performance data for Scott's method, both in the source water and the treated drinking water. And you can see, except for the very long chains, what is that, the 16 and 18 chain acids, we had really good recovery across the board. So, his method does work well. It works well in different matrices. It's just not an official capital M EPA method. So take from it that what you will. In terms of concentration, for all my figures, the green bars and green sections are going to be the source water. The blue is the treated water. For these box plots, the belt is the median concentration. The shoulders are the 25th and 75th percentile. The upper limit is the top whisker. Since this is a logarithmic scale, we couldn't plot a non-detect or a 0 for the lower limit, so we just put the different detection limits in there as the lower whisker. But you can see first the range of concentration. You know, this is a log scale, so we're looking at 4 orders of magnitude, 5 orders of magnitude, and some of these concentrations between the different 25 locations. So there's just the range of different concentrations that are out there in the environment. Additionally, only the ones that are bold: the PFOS, the PFAA, PFHEX-S, and the PFUNDA. So that's the 8, 7, 6, the 8 and 7. The 8 sulfonate, the 7 acid, the 6 chain sulfonate, and the 11 chain acid. Those are the ones that showed statistically differences between the source water and the treated drinking water. Everything else, across the 25 locations was statistically the same in the source water as the treated drinking water, showing the minimal removal that is going on in drinking water treatment plants. Now, I mentioned we had 6 locations that are along 2 river systems. So at the top, we have those on what we called large river A, again, anonymity. And they were dominated by PFOA in their water. You can see, 60%, 70% of the samples was PFOA for these samples. And these locations were a couple hundred river miles apart and were collected. Actually, utility 2 was collected in July, and the last one collected was utility 21. That was collected the following September. So, there was quite a range in terms of the dates of collection that this pattern persisted in this water system. Now, you compare that to large river B, that was primarily PFBA was the primary chemical, PFAS in those sets. Again, those samples were probably about 1,000 river miles apart, and again, collected over the course of a year. So, that river had a very, very strong pattern that continued downstream. At the bottom, I have 3 other locations: utility 4, utility 22, and utility 24, just to kind of show the variety of different patterns that were in some of the other samples. Utility 4 was the one that had the most compounds detected overall in the study. They had a lot of pharmaceuticals, those type of things detected, not as many PFAS compounds. Utility 22 had the most PFAS detected of any sample in our study. Again, it was PFPEA, the 5-chain acid, was the predominant compound in their samples. And utility 24 was a groundwater sample, just kind of showing you how different locations can have different things. And that one had a lot of the PFHEX-S in the sample. So to investigate some of these sources and where did the PFAS come from, we turned to the drinks model. And if you're not familiar with this, this is a model that was developed by Paul Westerhoff and his group at Arizona State. And basically what he did was model all the wastewater outfalls and how much wastewater those wastewaters produce, then drinking water intakes, and looked at the flow and the percent of these different locations. So he was able to calculate the de facto water reuse at each of the different locations, each of the drinking water intakes across the United States. And you see, some of these green dots and red dots. The red dots are over 15% wastewater in the source water. Green dots are between 10 and 15% wastewater. So, there's some of these locations that while it's not direct potable reuse going on, we are getting a lot of de facto reuse going on, that there's wastewater in these source waters. So we want to see how our data, because initially when I planned the study, I wanted to target locations that had a lot of wastewater in the source water because none of the texts are boring to look at. So I really wanted to kind of like peg the upper end of things. But, just trying to find this information, it wasn't available. This study was published after we'd done our samples. So we looked at his and looked at our de facto reuse percentage for the different locations. Now, these are ordered by stream reaches. So the 3rd order rivers are the smallest ones. The 8th order is some of the larger rivers. You could probably step over some of the 3rd and 4th order or 5th order streams. You definitely need a boat by the time you get to the 8th order and 9th order. But within these, they're ordinated by the DFR percentage in each one. So you can see some of these locations have, on average, up to 10% de facto reuse going on. And in some cases, in low water droughts, that type of thing, they may have increased de facto reuse percentage when the wastewater streams become a larger percentage of the water. So there's a lot going on this slide. So I'm going to try to unpack it pretty easily. So the top bar graph here is all organic chemicals that were in our study, their concentration, and it's ordered by these different stream reaches. Then below, I plotted the factor reuse percentage on the x-axis versus the concentration on the y, to try to get an idea if there's a relation between the two. So we had one location, utility 1. We had a lot of blank problems with that sample, so it had a really high de facto reuse percentage, but not so much in the chemicals. We had to censor a lot of out of our chemicals. So if we throw out that one outlier, the slope between the two ends up being 0.51%, or no, sorry, 0.3%. So then if we leave out the PFAS and we just look at the pharmaceuticals and the anthropogenic waste indicators, so those are things like fragrances, some nonylphenols, other things that we know are in wastewater, and do the same correlation, leaving out that one utility that's kind of screwed up, we end up getting a correlation of 0.51. So 51% of the concentration can be attributed or explained by the de facto reuse percentage. And that's, for a study not necessarily designed to prove that or look at that, it's pretty significant. When we look at the PFAS, again, I mentioned we had that utility 22 that was really high. Here's the other one. So regardless how we do it, if we throw out, we throw out utility 1, we throw out utility 22, at best we can get 0.15% relative standard deviation, or an R of 0.15. So, from this study, from the sites we looked at, the source of PFAS in these locations does not appear to be wastewater. It appears to be other types of sources to the water. What those sources are, we can't say, but it looks like it's not PFAS. And if you want to read about this more, it's been published in Journal of American Water Works Association in 2018. So looking at treatment, on the top, we have the number of PFAS that were detected in each location. So now on the x-axis, we have the different utilities instead of different compounds. And you can see, it's pretty consistent. It's mostly between 9 and 10, 9 and 12 different locations. It's, looks almost like a cut grass lawn. We have this one location that was a groundwater location that had much fewer PFAS detected in terms of the number of compounds than the others. But in all, it's pretty consistent. When we look at the bottom panel, the concentration, you can see that the pattern was much more diverse. And again, we have to have the log scale here just due to the wide ranges of concentration. And we have some utilities, like utility 2, that's showing some removal. And we want to kind of tease out, why. And again, the study wasn't designed to look at treatment. It wasn't designed to really, pin into what's removing PFAS. But granular activated carbon is, in the literature, is one of the main sources of PFAS removal in drinking water. And we looked at the utilities that said they used GAC in their treatment trains. On the top, we have the depth of the beds that they have, and at the bottom is their recharge rates. And you see utility 2, they use a very, very deep bed, and they also recharge it quite frequently. So they're having their carbon is very active, so it's able to remove PFAS, where some of the other utilities are going decades almost between changing out their carbon beds. So across the study, we only had 4 locations: utility 2, utility 3, utility 18, and utility 25 that showed statistically different removal between the source water and treated drinking water, most likely due to their carbon beds. So kind of the so what question is, we've measured PFAS now in these drinking waters. Do the utilities, do the customers need to be concerned about that? And if we use the current US EPA health advisory level of 70 nanograms per liter, which I have the line struck across there, only one utility exceeded that for their sum of PFAS, or PFOS and PFOA, and that was at utility 22. So for all utilities, we gave them all their data before we released this to the public and before we published it, so they knew. And we had various meetings with the different utilities to talk about their data for either PFAS or for any of the compounds. Some had questions about the microbe reading, some of them had questions about some of the pharmaceuticals. So, we really worked with the utilities to let them know what we wanted, what was going on from our data set in their water. But with the utility 22, I was really kind of curious to see, what happened in the future. And it just so happened that the UCMR sampled after our sampling event. And for those of you that don't know what the UCMR is, it's the Unregulated Contaminant Monitoring Rule. It's a tool that the Office of Water has to look at chemicals and microbes in drinking water samples to determine if there might be a need to regulate things. So every 5 years, they can go to every drinking water treatment plant that serves more than 10,000 people, and they do a statistical subset of those that serve under 10,000 people. And they can analyze them for no more than 30 different chemicals. So, it's kind of a really small list that they're able to look for. So in UCMR 3, which was conducted, I think, between 2013 and 2015, 6 of the different PFAS that were in method 537 were on that list. And then, as I mentioned, in phase 2, we had 17 different compounds. But so UCMR used 537, the old school original one. As I mentioned earlier, that it had much higher method detection limits of 10 to 90 nanograms per liter, where we were, at sub part per trillion levels. And that's just, simply a matter of the robustness of the methods needed. My office mate, Jody Shoemaker, is actually the one who develops the different drinking water methods. She did 537 and 537.1. And she's the one that really, really hates the term modified 537 because, if it's not 537, it's not 537. But, it's basically, she has to design these methods to fail. So basically, she does everything she can to break it and then, put in a method, this is how you break it, so don't do that. So she tests every single different vendor of carbon. She tests taking things to dryness, all different ways of, what can you do for this method to do it wrong, and she finds that. So, pretty much the method Scott developed is an art. He can do it in his laboratory and his instruments, but his method may not be able to be transferred anywhere else to get as good of data as he can get. Jody's method, in theory, can go transfer to any method, to any laboratory, and get the same level of data she did. So, it's 2 different methods, 2 different things. I don't want anyone to think that I'm disparaging 537 because I'm not. It's a fantastic method. It's just not, it's designed to do regulatory purposes. It's not designed for research. So I hope everyone's clear on that now. So, okay. So comparing the UCMR data to our data, I was able to go through and find, well, that's the next part, sorry. So looking through UCMR, as I mentioned, they go to every drinking water plant that samples, or that serves more than 10,000 people in the subset, the sub serves under. So there was, nearly 5,000 plants, 4920 plants that they sampled. And their detection frequency was at most 2%, for some of these compounds. But they did get, a larger number of those above the reference level of the 70 nanograms per liter for either PFOS, PFOA, or their sum. Whereas in our study, we only looked at 25 plants, but in most cases, we had at least 80%, if not higher percent, of detection for the 6 that were part of the UCMR method, or UCMR study. And we only had the 1 location that exceeded. So, but the most important things that to point out is that, the lower detection limits that we had did lead to a higher frequency detection. But utility 22, between our study and UCMR 3, no longer had detectable levels of PFAS or PFOA in their samples. So I'm not quite sure what happened between there. I don't know if they changed, something happened in the source, that the source was cut off, or if they changed their treatment, because that is one limitation of the UCMR. They only look at finished water, they don't look at the source water, so we can't account for either way. But regardless of the difference, utility 22 was not experiencing those high levels that we monitored in our study. So good news for utility 22 community. Just we don't know what changed there. So as I mentioned, we sampled 25 source and treated water pairs. And the big thing in this study was that all 50 samples that we collected, we did have measurable amounts of PFAS in those samples. We had the one that exceeded the health advisory guidelines. But as I mentioned, over time, that was no longer a problem. We had those distinctive PFAS patterns on those 2 large rivers that kind of showed that PFAS does persist downstream, pretty much unchanged in the different locations. PFAS is not as strongly linked to de facto reuse percentage as some of the other contaminants of emerging concern that we looked at in the study. So it suggests that there's non-wastewater sources, but again, we can't comment on what those sources may be because we didn't study those. Across the board, there's minimal removal of PFAS during drinking water treatment, but granular activated carbon does appear to be effective in treating it, especially if it's a larger bed that is frequently regenerated. And the detection frequencies in our study were higher than those in UCMR, but again, that's just due to our detection limits. So with that, I want to thank you for your attention.
Dr. Small, you.
Oh, I don't know how to pull this. While she's getting that ready, let me just ask, how many people here are regulators? There are a number of regulators. People working in solid waste. Drinking water treatment. Wastewater treatment. A lot, okay. Engineers? I know, find my cursor. I know. Geologists? All right. So I'm going to talk to you about the EPA PFAS Action Plan update, data analysis, and the tools preview. Let's see. We'll start with the PFAS Action Plan. And just those of you folks here probably know the history of the PFAS Action Plan, but basically EPA convened a two-day national leadership summit. We had governors from many states, high-level folks, and we also hosted PFAS meetings, community discussions around the country with impacted communities, and we sought public input. And out of 120,000 comments submitted to the public docket, as well as the results of those meetings, the PFAS Action Plan was born, a multimedia, multi-program national research, management, and risk communication plan intended to assist states, tribes, and communities in addressing PFAS. So it basically is a plan for what EPA is going to do and gives us, folks like Susan and me, the permission to actually go out and do some work on this important issue. So I'm just going to whip through the various actions that we've promised to undertake and give you a quick status update on those. Within drinking water, we committed to following the MCL rulemaking process. I think many of you know that's a long process. So don't expect an MCL real quickly, but we are following the process. It also doesn't guarantee that there will be an MCL, but we are going through that process. As a next step, we intend to propose a regulatory determination. I saw email traffic this morning. They've just released from headquarters that, in fact, that regulatory determination and draft has gone to the Office of Management and Budget, which is the next step in the process, and it may actually happen by the end of the year, as it says here in this bullet. It's been promised by the end of the year. So that's a positive step, and that regulatory determination would actually give EPA some teeth and an option for having a regulatory hook, and that would allow us to help back up the states on the efforts that they're taking. The agency is also gathering and evaluating information to determine if regulation is appropriate for other chemicals in the PFAS family. I know we've been talking about a lot of different PFAS chemicals here, so I think that's an important step. For surface water protection, we're developing National Clean Water Act Human Health Aquatic Life criteria as data allows. Data is somewhat sparse, but we're getting there. EPA is examining available information about PFAS released into surface water. Susan's given us some of that information already today, and determining if additional study is needed for potential regulation. We're also proposing nationwide drinking water monitoring under UCMR 5. And so we typically only put chemicals on the UCMR list one time, but we're gonna put PFAS on second time. And I think we're gonna have more compounds this time around. Hasn't been finalized yet, but 2022 to 26 is when that round of sampling will happen. Again, we're not gonna get the information real quickly, but we are gonna get more data eventually. Under the toxics banner, we sent 2 actions to address PFAS to OMB. That's mainly putting PFAS on the toxic release inventory and also putting limits on importing new imports of PFAS. Advance notice of proposed rulemaking for TRI, that's already gone out, and so public comment is imminent. Supplemental proposal to ensure that persistent long-chain PFAS chemicals cannot be manufactured or imported into the U.S. without notification. So they can still come in, but we need to be notified under TSCA. I think one of the significant things here is the toxic release inventory. If we can get PFAS tracked through toxic release inventory and get a better handle on who's using it and how much, I think that's going to help us understand the distribution of potential sources a lot better. Risk Assessment Integration Information System, also known as IRIS. I'm sure you're all familiar with that. And we've released some systematic review products and protocols for various compounds, and we're slowly working through the risk assessment process for these chemicals. Biosolids, we're developing risk assessments for PFOA, PFOS, understanding potential health impacts with biosolids. I know states are looking at that too. We are using enforcement tools when we can or when appropriate to assist the states at this point. If we get that regulatory determination and this is found to be a hazardous compound under CERCLA, we'll have a stronger hook, particularly for remediation and those types of things. And we're working to develop a risk communication toolbox, because I think risk communication is a huge issue for PFAS. I mean, I think everyone's really concerned and has a lot of big questions throughout the public that we serve, and so risk communication is a big part of what we need to work on. So we are working to get some tools that you can use for that. Cleanup, interim recommendation for addressing groundwater contaminated with PFOA and PFOS. I saw a draft of that just go through email this week, so that's will be released imminently. We're initiating regulatory development process for listing PFAS as a hazardous substance. I mentioned that already under CERCLA. Here's a variety of research that we're doing. I'm not going to read you the whole list, but you can see the kinds of things that we're doing, developing new test methods, exposure models, some of the things we've discussed today, tools to assist officials with cleanup decisions, we've also spent a bunch of money recently and put together a whole package of research under our STAR grants program to look at solid waste and wastewater treatment and a variety of approaches for addressing PFAS contamination in those areas. So we're putting a lot of effort into the research arena. All right, that's just a quick overview, and I would say that, you know, the real focus for this document is to help back up what the states are doing, because states like California are really stepping up and doing a lot and moving this issue forward. So next I would like to shift gears and talk about Guam. One of the presenters earlier today said, what leachate is the definition of matrix interference? Well, Guam is the definition of a single source aquifer, right? It's an island and there is no alternative supply. They've got an aquifer and that's it. And if you've got PFAS in your aquifer, it's a big problem. So we decided we were gonna try and help Guam and do a quick vulnerability analysis to try and better understand a basic question. If you had some more money to sample your wells, which wells would you sample first? And that's really what we were trying to understand. Pretty simple question, pretty simple analysis, and as I go through it, you'll see some of the things we dealt with, and it may apply to efforts that folks undertake in the future. Let's see, is this a, can you see? No, laser pointer? Oops, oh yeah, here we go. Which one's the laser?
Yep, we got
that little button?
Yes.
There we go, sorry. I switched slides inadvertently. Okay, so on Guam, I did it again. This button, Matt, all right. So on Guam, this is kind of the coralline aquifer right here, coralline and volcanic sediments. This is a more mountainous region. This is the volcanic portion of the island. So if you've never been to Guam, it's kind of volcano and then coral and volcanic sediments here. This is their aquifer. And so what's interesting about Guam, when they went out for the UCMR3 sampling, each well has a treatment system sitting right on top of it. So the wellheads and the treatment systems are one-to-one. A lot of other areas, when the UCMR3 sampling was done, say in California, Southern California, they sampled the intake to the drinking water treatment plant, right? Well, you don't know where that water's coming from. Is it groundwater? Is it imported water? You know, is it local? Is it, you know, does it come through from the canals from Northern California? So this was very unique in that we knew if we had some type of a presence of PFAS in one of these wells that were sampled, it was in that well, in that location. And you can see here, that's all this bar chart is showing you, roughly a one-to-one correlation of treatment facilities and wellheads. Okay, I really did mean to change slides that time. So here's where we had our, doesn't show up very well, I'm sorry. This is one of our detections here, and this is right next to the municipal airport. We have a couple detections here in a more industrial area, and then a couple, and fairly high, and then a little bit lower detections here in an area that really doesn't have much industry, and we're not quite sure where those came from. You know, maybe there was a fuel spill on the highway or something, and they whipped out the firefighting foam, just don't know. So you can see here that UCMR3 sampled a number of these wells. They had a lot of sampling. And I should show you, this is Anderson Air Force Base. No detections at Anderson Air Force Base, interestingly. But they used to use this airport actually for the Air Force previously. All right, so this is showing you all the potential sources, and we tried to be more inclusive than exclusive. And on the island of Guam, the majority of potential sources are DoD facilities. And then we had other things, plating shops and furniture and textiles and things like that. But the majority were DoD facilities. Honestly, we grouped them all in there, but I don't know if it's a warehouse full of PFAS or a, you know, an office building full of people on the phone. So we were, again, we're more inclusive with our potential sources than exclusive. Again, a simplified analysis: airport, airport, fire training facility, fire training facility. Okay, and we we ranked these slightly differently if we knew that there was a real potential problem. All right, next slide. So we did just a real quick first cut. We just did a heat map of the potential sources. And the hotter areas are where we've had detections. And these little circles are showing where we've had the detections. So that was our first cut at doing some sort of vulnerability assessment. So if we looked at this and we wanted to go out and take some more samples, I might sample up here, over here, some of these areas where it's a little more orange. Then we did something a little bit more loosely geologically, hydrogeologically related. We basically drew Dixie cup circles around the wells. We did a wellhead protection area analysis, essentially. You can see the kinds of simplifying assumptions, but we basically treated every well the same. They all have the same pumping rate. They're sitting in a big sandbox. There's no interference between the pumping of the wells. And then we looked at various circumferences around the well and looked at the distance from sources within each of those circumferences and calculated a vulnerability for each ranking based on number of sources times the weighting factor divided by distance from the well. Pretty straightforward type of analysis. And when we did that analysis, we get a little bit more resolution on where we might want to take samples. You can see where our detections were, again, these red circles. And so again, I would probably take samples up here, maybe over here. In fact, we took a sample up here, or Guam took a sample, I should say, and they actually had a detection. So it was interesting that they were able to go out and verify some of the results from our model. However, I will caveat that with saying that that was a thing called a Maui well, which is essentially kind of a horizontal tunnel. It was just waiting to get contaminated, really. It ran under a highway and some other things, so it may not really be a fair test of the model. The model also, we said, it doesn't show any vulnerability down in this area, though we know we've had detections. So what we did is we actually took the known detections and put them in as potential sources within the model. And that's the results we got here. Things start to rank a little higher in this vicinity once you see that we've incorporated known detections. These pie charts show high, medium, and low vulnerability. High, medium, and low vulnerability. And you say, Matt, how did you determine high, medium, and low vulnerability? Well, we just saw some natural breaks in the data and natural groupings in the data, and that's what we use for high, medium, and low vulnerability. You can slice and dice it any way you want. We have enough money to sample 10 wells. I can tell you the top 10 wells, and those will be the highest vulnerability. So it's really a ranking, and you can slice it any way you want, but the thing to notice is that when we added those additional detections in as potential sources, we got more medium and more high ranked vulnerabilities. So again, this is a very simplistic approach to this type of analysis, but I think it's a good first cut. I'd like to go, the sources definitely need more refinement. That's the weakest and most uncertain potential or input parameter in the model. I think the vulnerability analysis correlates relatively well with what we know about the business and industrial areas on the island. Sampling is really needed to verify vulnerability analysis. And as I mentioned, that one sample, which was sort of a funny one for the Maui well, did show a detection. And I think the existing model could be used, but it shouldn't be used alone. It should be used along with information from the regulatory agencies and the water agencies. And I'd like to work with Guam to improve source definition, sample some wells, additional wells, validate the model and the approach in other locations in Region 9. And I'd like to use a more detailed flow model. It's a little unrealistic just to draw circles around the wells, particularly when you have so many pumping wells in the vicinity of each other. The flow regime is probably pretty complicated. And I'm going to start working on some fingerprint analysis for these folks. Those are our basic next steps on this effort. So, last section here is we are working on a EPA National PFAS Data Explorer. It was supposed to be out this month. I think it'll be out next month. It'll be a publicly available data explorer. This is what it'll look like. And it's built on our data analytics platform, which is built on Qlik, Q-L-I-K, and it has a whole bunch of cool functionality. So when you bring up maps and things like that, if you click, for example, on one of these bar chart bars, all of the other graphics adjust to show only the data from that bar chart bar, or you can click multiple bars. It allows you to really interactively browse through the data. We've got all these different, we've got an integrated map, we've got drinking water, production, enforcement media, discharge monitoring, we've got all these different types of maps you can look at. And once you whittle it all down and do the kind of search that you want to do and build your visual query, you can download the raw data for anything that you have displayed. So it's going to make a lot of data, national level data, available to everybody. Coming soon to a web browser near you. All right, thank you so much.
Should be the one with the SWRCB. Yeah. All right, wonderful. Thank you. Thanks all. Thank you guys, Dr. Matt, Dr. Susan. I think one of the big takeaways for me is that as the science and the source investigations and the regulations are starting to really ramp up on these compounds, the litigation is following suit. I mean, the issue for us is who's going to pay for the PFAS in the wells of the public water suppliers like on Guam. Start off with an apology. I am not Mark Ruffalo. He's bummed that he couldn't be here today, but you guys are going to have to settle for me. Again, my name is Tim Sloan. I'm an attorney at Scherer Edling LLP in San Francisco. Today I'm going to talk a little bit about PFAS use and release to the environment. I think I'm kind of preaching to the choir on that issue, so I'm going to gloss over those slides a little bit, but the main point of that will be that PFAS are ubiquitous at this point in the environment, and there are loads of point sources that we are thinking about how to address with litigation and whether or not that's the right way to go about addressing that PFAS. Follow that with a brief look at PFAS treatment and costs, and then try to answer the question of who pays for the PFAS that is in the environment and particularly affecting public drinking water supplies, and why the entities that we're suing for our clients we think bear responsibility. And then I'll walk a little bit through litigation that's going on right now and how we would go about doing that. So as I said, our focus at Scherer Edling is public agencies. It's all we do. We represent, particularly in the groundwater space, public water suppliers that are dealing with PFAS, 1,4-dioxane, especially out in Long Island, and 1,2,3-TCP and hexavalent chromium in California. And kind of our firm ethos is to put liability on the higher up institutional actors that we feel are really responsible for the eventual release of PFAS to the environment. And by that I mean the large manufacturers at the top of the supply chain who were sophisticated and had the knowledge about these compounds, and rather than sharing that with the world, instead kind of kept it under wraps. And now we have ubiquitous PFAS in the environment. The focus of our litigation for public water suppliers is typically to cover the cost of investigation, monitoring, and adding treatment, and then operating that treatment over the future as necessary, so recovering those costs for our clients. Again, I think I'm going to gloss over these slides a little bit because we're all in this room aware that PFAS are ubiquitous in the environment. This is just a table from the Interstate Technology and Regulatory Council that kind of tracks the timeline of some of the perfluorinated compounds, their development and use. Takeaway here is that these compounds have been in development since the 1930s, so at least 80 years they've been in the commercial sphere and being used, and I think, you know, in large part because we didn't know, ignored in making sure that we remove them from waste streams. So that's kind of where we find ourselves today, is 80 years of pollution, and now we're only just kind of catching up to that issue. This flow chart is kind of an illustration of the general movement of PFAS from manufacture to disposal in the environment, and the takeaway here is the kind of the call outs in these bubbles. I don't know if you can see them very well, but they kind of list different uses of PFAS. At each bullet point, it represents a secondary product from which PFAS might be released at the point of manufacture, use, or disposal. So as you can see, the kind of possibilities are endless with these compounds. One of the major examples in California, or excuse me, in the United States, and that's a focus of the litigation that's kind of going on across the country right now, is aqueous film-forming foam. This is the foam that's used at commercial airports, military facilities, and other institutions to put out kind of more severe fires, typically hydrocarbon-based fires. This stuff was typically manufactured to military specifications, so there's a lot of government users. The military bases in particular, I think EPA has done some work on identifying which of the bases were using the AFFF, and I think this map up at the top right kind of illustrates that, you know, we have airports everywhere in the country, which means at a certain point, if there's training with AFFF, you're going to see AFFF in the groundwater near those airports. Another look at the PFAS life cycle, but I think I'm going to skip over this one. The major exposure pathways for these compounds that we're thinking about in particular is drinking water for my clients, but there's also ingestion through fish or seafood or homegrown produce that was watered with contaminated water, incidental soil or dust ingestion, and potentially, if you're exposed to really high levels of this stuff, dermal absorption or inhalation. Skipped one. Coming out of both the litigation and the research on these compounds are a kind of host of diseases that are potentially linked to PFAS. Cancer of the kidneys and testicles, thyroid and liver disease, asthma, cholesterol. You know, it's a pretty broad swath. So what we're seeing in addition to litigation around drinking water supplies is personal injury and medical monitoring litigation. And then this slide illustrates that, you know, public drinking water suppliers, pursuant to the UCMR3 monitoring that went on, discovered that PFAS were a problem across the country. I will say that this blue and gray map on the top right is kind of out of date because of the higher detection limits in UCMR3. We really didn't get a full kind of understanding of how broadly PFAS were distributed among public water suppliers, but what our clients are finding is now that EPA 537.1 is giving them the opportunity to test at lower levels. Essentially all of our clients are finding that they've got PFAS at some level in their systems. So as Susan mentioned, the effective treatment for PFAS in water supplies is granular activated carbon. It's an economical method. It's pretty straightforward. It's passive. It's known. It's not novel. It's not cheap, but it's not, you know, an unproven technology. One of the things that some of our clients are dealing with other emerging contaminants like 1,4-dioxane is having to install kind of novel treatment systems. They're using advanced oxidation process in Long Island to address 1,4-dioxane, and it's an expensive endeavor. Granular activated carbon, this is kind of an estimated treatment chart or cost per treatment chart, looking at a couple different well sizes. I think the upshot here is that, you know, you're looking about $12 million to operate a GAC system on a 1,500 gallon per minute well over about 40 years, and that's capital and operations and maintenance costs. for a lot of our public water suppliers, $12 million is not an easy sum to come by. And the question that's kind of presented to us and that's fundamental to litigation is, who is going to pay for that? Should the ratepayers have to bear the cost of perfluorinated compounds in their water, or should we put that on the polluting entities, the manufacturers that are responsible for it? So I'm going to move into who those culpable parties are. This graph, not nearly so scientific as the doctors next to me, kind of illustrates the tower of knowledge, which is just kind of an approach for us. Ratepayers down in the bottom left, they have the least ability to pay and the least amount of culpability for why perfluorinated compounds are in their water. And as you move up, what I'll show you is that with, particularly with the major manufacturers in the US, 3M and DuPont, they had the knowledge, they were the sophisticated researchers who understood that these compounds were going to get into public water supplies. And for those of you who stick around for the documentary and maybe go out and see Dark Waters, you will really get that kind of thrust right in your face. So this is kind of looking at potential defendants. On the PFOA as a raw material side, we've got DuPont and 3M, and then there were certain other telomere-based AFFF manufacturers who were also producing this stuff with knowledge of the potential groundwater impacts of these products. But I'm going to focus on DuPont and on 3M. We have a wealth of information about what DuPont and 3M knew and when they knew it based on litigation that's already kind of run its course. So in particular, a case out of Parkersburg, West Virginia. This was the class action and public drinking water supplier case that was the foundation for the Dark Waters movie, in which the lawyer Rob Bilott, who's played by Mark Ruffalo, he kind of delved into, he encountered a farmer who had some cows dying, and they got to the bottom of it, and it turned out that DuPont was dumping perfluorinated compounds into a landfill site that they leased from this farmer. They sued. That case eventually settled, but Mr. Bilott was undeterred and decided to go after these guys from on behalf of public water suppliers and some personal injury cases as well. And that case ended up settling in 2004. There was an initial settlement in which DuPont agreed to fund an epidemiology study, which identified 6 ailments that are potentially linked to perfluorinated compounds, or that are now linked to perfluorinated compounds. DuPont is now dealing with individual personal injury suits for those residents downstream of the Parkersburg plant who have those injuries, who have those ailments, and are needing to pay for their medical care. This memo is from the DuPont toxicology chief in 1961. All the way back in 1961, DuPont was aware that the C8 and C9 products should be handled with extreme care and contact with the skin should be avoided. And this is a March 1981 DuPont memo to managers on their industrial plants, in which they were advised of a 3M study showing birth defects in fetal rats exposed to PFOA. DuPont immediately told its managers to pull female workers off the floor of areas of the plants that were potentially PFOA exposure areas. And then fast forward to 2000, when DuPont is starting to deal with the fallout as this knowledge is coming to light. They have an internal staff meeting of lawyers and PR folks and some heads of the company. An email coming out of that meeting, a lawyer writes, "Our story is not a good one. We continue to increase our emissions into the river in spite of internal commitments to reduce or eliminate the release of this chemical into the community and the environment because of our concern about the biopersistence of these chemicals." So back to 1961, all the way to the present, DuPont knowledgeable about the potential effects of these chemicals. Same is true of 3M. This is a 1978 internal toxicology study that 3M researchers conducted, in which they accidentally dosed rhesus monkeys, overdosed rhesus monkeys with C8. All those monkeys died within a few days. So the toxicological effects were well known to 3M by 1978. So this is actually a kind of aggregation of 3M's internal research that it put together in 2000, in which it references studies in the 1970s where 3M was investigating the environmental fate and transport of perfluorinated compounds. They eventually disavowed those studies. They said the science wasn't robust enough, but you better believe that 3M was aware that these chemicals were leaching out of their landfills by the 1970s. And then finally, probably the most damning of the documents that have gotten into the public sphere is a resignation letter from a 3M environmental specialist who is just disgusted with 3M's handling of PFOS toxicity and its malfeasance in informing its customers and the public about the potential toxicological effects of these chemicals. He writes, "I have profound disappointment in 3M's handling of the environmental risks associated with PFOS. 3M waited too long to tell customers about the widespread dispersal of PFOS in people in the environment. And at almost every step, I've been assured that action will be taken, yet I see slow or no results. I'm told that the company is concerned, but their actions speak to different concerns than mine. It is unethical to be concerned with markets, legal defensibility, and image over environmental safety." So those are, that's kind of the backbone of the litigation. That knowledge is enough that these companies should be held liable for the release of their chemicals into the environment. So kind of the overview of the litigation right now, it's nationwide. There are a host of different types of cases, which I'll kind of walk you through. The major issues that we're looking at are causation. Where did the PFAS come from and who does it belong to? That's going to be something that's going to require expert testimony, both on the environmental fate and transport side and also on the chain of commerce side. Injuries, we're looking at least through the lens at Chair Edling, we're looking at public water suppliers. So again, those costs of investigation, monitoring, and treatment. One of the major issues that is going to pop up in this litigation across the country is the government contractor defense. This is an absolute defense to liability where a company like 3M or DuPont says, look, we were manufacturing this stuff to the government specification. The government was controlling how we made these products, so we shouldn't be held liable for what the government was telling us to do. I think the major issue that's going to come up in resolving the government contractor defense is whether 3M and DuPont and these other AFFF manufacturers were actually informing the government of the dangers that it knew about that the government may not have been aware of. And that's something that really hasn't been explored in the litigation to date, namely because the major two cases that I was just talking, or the major case I was talking about, Parkersburg, and then Minnesota, the state of Minnesota's case against 3M, both of those were point source cases where 3M was discharging, and the discharge was the culpable conduct. When we talk about failure to warn, which I'll get into, I think the question there is going to go back to whether the government is going to provide a shield to these defendants. Some of the claims that are currently being litigated right now are under RCRA, CERCLA, common law, and particularly products liability cases. I'm going to walk through each of these. But with respect to our public water suppliers, the biggest issue for us is establishing an injury. So especially where there's no MCL, sometimes it's hard for a water supplier to kind of wrap its head around how am I injured if I don't have an exceedance. But what the Second Circuit has said about this is that state maximum contaminant levels serve as a guidepost, but don't define whether there's actually an injury. And by guidepost, it means that suppliers can sustain an injury without the presence of an MCL, so long as they're taking reasonable action to respond to contamination in their wells and that they've got a public health reason for doing so. That constitutes a cognizable injury for which they can get, they can recover. By way of MCLs, we don't have one yet in California. I know there's some notification levels that the Department of Drinking Water has set forth, and that's all kind of a prelude to MCLs here. MCLs across the country are looking in the low 10 parts per trillion levels. New Hampshire proposed a 12 part per trillion for PFOA and 11 parts per trillion for PFNA. New York has proposed 10 parts per trillion for both PFOA and PFOS. Vermont has 20 parts per trillion for combined 5 different perfluorinated compounds. So, the MCLs that are coming down are low. What MCLs do provide for us is a bright line injury. If you do have an exceedance and your state drinking water agency is telling you that you have to add treatment to your wells, then absolutely there's a cognizable injury that you can litigate in court. RCRA, this is a cause of action that's typically directed more at point source discharges. The idea here is that plaintiffs would need to establish that defendants contributed to the handling, storage, treatment, transport, disposal of PFAS in a manner that resulted in an imminent and substantial endangerment to health or the environment, which is a bit of a mouthful, but something that I've memorized. One of the major hurdles in establishing a RCRA claim is that contribution element. So we have to show that the defendants contributed to those activities I listed. The courts have interpreted that as requiring some sort of active involvement in that handling, transport, treatment, or disposal. So to try and pin it on a 3M for their superior manufacturing knowledge sometimes is a little harder to do. But this certainly works where you have a local discharger who actually did handle or dispose of those compounds. CERCLA, another cause of action that's being litigated around the country, a little bit more slowly because PFAS aren't themselves listed as hazardous substances, but apparently EPA has allowed PFAS ARARs to be implemented at remediation sites. So once you've got a cost recovery for an action at a site that's being remediated, the remediator will be looking at PFAS if there are applicable standards. And addressing that PFAS through the remediation process is a recoverable expense. Common law claims that we're looking at, this is kind of where we get more into the manufacturer side of things. Nuisance, we have to show that the defendant breached a duty which caused the plaintiff's harm. Here, the duty would be to put products on the market that you know are safe, and if you know that they're not safe, you shouldn't put them on the market. Kind of similarly, you can breach a duty to warn about known dangers of your products. So that would be kind of the foundations of a negligence claim. Trespass claim, that the defendants had substantial knowledge, or they were aware of the likelihood that their products would end up entering another person's property without their permission. This has been used successfully in the groundwater context where contaminants enter public water suppliers' well zone capture. That is grounds for a trespass claim. And then products liability claims, which are similar to the negligence claims. We would show that the defendants put unreasonably unsafe products on the market, or that they failed to warn about dangers known in their products. But unlike the negligence claim, we don't have to prove that the manufacturers had a duty to either warn or put those safe products on. It's kind of just established through law that they had that duty and that it was breached if the products are found to be defective. Probably the big thing that's happening in PFAS litigation right now is in this multi-district litigation in South Carolina. These are all the federal PFAS cases that have been consolidated before Judge Gergel. There are about 100 actions in the MDL. They are ostensibly all AFFF cases. The MDL was designed to host only AFFF cases, meaning that if you have a point source case that doesn't involve AFFF, it's ostensibly supposed to stay in your kind of area where you filed the case. But what we're finding is that the panel that oversees how these cases get consolidated into the multi-district litigation is tending to move them into the MDL. I think what we kind of foresee is that the MDL's scope may be expanded in the next year or two to encompass non-AFFF cases. But know that if your PFAS litigation makes it into federal court, it very likely will get transferred into the MDL. And again, just to reiterate, our goals of PFAS litigation is that polluters should pay, not ratepayers. We're looking to recover treatment costs, capital costs, and operations of maintenance, costs of any other interim non-treatment responses like purchasing surface water or other alternate supplies, costs of any investigation and monitoring, and any other PFAS-related costs. And with that, I'm done.
Any questions for the panelists, please?
Hi, Erica Calve from the Regional Water Boards. I have a couple of questions, but I'll ask Matt, because I've been really curious about the listing of PFOS and as a hazardous substance, and kind of what the process is, which PFOS might be included, if it's just PFOS and PFOA, or if it'll be more class approach, and kind of what the timing looks like.
Yeah, I really hate to do this to you, but that's all kind of internal at the moment. So it's with OMB, and I'm hoping that it'll come out by the end of the year, and your questions will be answered. But I can't really give the details at the moment. Sorry.
Hi, I'm Andrea Ventura with Clean Water Action. I have two questions for Mr. Sloan. First of all, the simpler question, I'll ask them both and then let you speak to them. The simpler question is, with these MDLs, as we're learning in California about PFAS in our water systems, if decisions are made in those cases that is going on now, does that leave everybody else out in the future? And my other question is, you mentioned about the GAC as the way of treating PFAS, but my understanding is that may be very effective for long-chain PFAS, but as we are learning more and more about the emergence of short-chain PFAS, GAC is not going to do it. The costs are going to be more expensive. And how are you handling that, knowing that it is very probable that many of these systems that you're representing are going to have to address that later, and might want to be investing in some of that treatment earlier on so they're not adding more cost and aggravation to their process?
Well, I'll take your second question first. So first of all, the big caveat is I'm not a scientist. I wish I could tell you more about GAC's effectiveness, but I think the thought is right on. Our clients need to be prepared to deal with these broader suite of perfluorinated compounds than just the PFOA and PFOS that they have emphasized in their investigations and monitoring to date. I'm not sure what sort of treatment would be more appropriate for that, but it's certainly something that we would investigate in the litigation. And to the extent that non-PFOA, PFOS perfluorinateds end up either getting regulated or rise to the level of any of our clients' drinking water supplies where they know they're going to have to add treatment for them, that would be something that we could address in the litigation, even if it's already filed specifically for PFOA, PFOS. We could amend the complaint and address a broader range of compounds. We could seek broader relief when we get to trial in any of these cases. And I would think that in resolving these cases, either through trial or settlement, we wouldn't foreclose the opportunity to bring claims down the road for the same client for other perfluorinated compounds. So it's not like we're foreclosed from doing that. With respect to the MDL, discovery is ongoing in the MDL, so there are elements that will be more or less, resolved in that sense. Facts will have been traded back and forth, but kind of the idea of a multi-district litigation is that you consolidate for the purposes that are common to all of the cases, and then when you have uncommon issues, those issues go back to the home court where the case was either originally filed, or if it was filed in a state court, removed up to the district court in that state. If I understand your question, I think a lot of the issues that would be unique to public water suppliers that maybe aren't in the MDL yet could eventually get litigated back in their home courts.
Hi, this is Jenny Larrabee from Valley Water, and I had a question for Dr. Glassmeyer about the utility that you mentioned that employed GAC and saw a noticeable decrease between, raw influent water and finished treated water. It looked like I thought you mentioned that several other utilities also employed GAC, but yet you didn't seem to see as much of a difference between influent and effluent. Did you explore that further, or am I misremembering the data?
So yeah, so on that slide I had about 8 different utilities that use GAC. There was 4 that showed statistically significant difference between the 2 of them. I mean, utility 2 was the only one on the slide before that showed a visual difference, but the others showed statistical significant differences between the different compounds.
So, okay, so you can make the general statement then that GAC did tend to reduce. Okay.
Yes. But that utility 2 that did have the significant removal, they had, about 3 times greater than any other utility's bed, and then plus they recharge it like twice a year. So that's one of the reasons why.
Could I ask a real quick question while we're on GAC of Tim? If if people are using GAC and getting paid for GAC, but then that GAC is being put in a landfill or going to incinerators where it may not be fully destroyed, what's the liability for your clients at that point when they've asked for relief, and then this relief actually may give them additional liability?
I actually have been trying to track that down myself. I think kind of the question you're getting at is, what do you do with the carbon once it's pulled out of the GAC vessel? Because at least from what I've found, kind of the normal regeneration process doesn't remove PFAS, right? I don't think we incinerate the GAC to a hot enough level that it's going to thermally destroy everything that's in there. So that would be a cost of treatment, and it would be a cost that would be put on to the defendants to the extent that we would prove at trial that not only is GAC necessary to remove the perfluorinated compounds from the water, but also our operating and maintenance costs have increased to operate that sort of treatment system because of the perfluorinated compounds. That would be a recoverable expense.
Hi, my name is Evelyn Wendell from WETAP, and I have a question for Matthew. Can you talk a little bit about the risk communication toolbox? Can you elaborate a little bit about that?
I'm sorry, I don't have a lot of details on it, but I think, the big thing that we're trying to focus on is risk communication to the public. What people can do to protect themselves, what they can do to inform themselves, how they can work with their local water purveyors to better understand the issues, and then make those tools readily available to state and local regulators so they can use them to help communicate with the public. So that's really what we're aiming for at this point.
Do we have a question?
When will it be available?
Yeah, when will it be available? We already have some of that information on our website. It's epa.gov/PFAS. Pretty easy URL to remember. So go take a look, and there's fact sheets already on there explaining a lot of the information that's available. Some of them are fairly technical still. So I think a big focus that we have for this risk communication toolkit is to take a lot of what we know and put it in more plain language. So, but there's a lot of good stuff there already.
Hi, I'm Kathy Swanson. I'm from Purolite. We're an ion exchange manufacturer, and I've worked for a GAC company in the past, so I can answer a little bit of the questions that you guys are asking about. So GAC, when it is reactivated, it's heated up, the chemicals volatilize, it goes to an afterburner where the PFAS is destroyed for the most part. There is a lot of data that does show that ion exchange can be more effective at the shorter chains, especially when it comes to PFBS. It's extremely effective at anything with the S, the sulfonate on it, so the PFHXS is another one that it's extremely good at removing. And it works for a longer period of time than GAC, and you use less of it. So, I've done a lot of comparative analyses where I've found that ion exchange, a PFAS selective ion exchange, is actually less expensive than GAC because you just burn through so much carbon. Now, I will say that depends on the water quality. It's always going to depend, and we really need to analyze that water quality to make sure that, that's right for you. But, that is a good option, and it has been shown to be more economical for a lot of water utilities.
Do we have a question, Jacob?
Yes. This is from one of our online audience members. This is to the EPA reps. What is the chance that PFAS will be identified as a hazardous substance as either part of a regulatory action or as inclusion in the National Defense Authorization Act? If it does, how does that change the regulation of PFAS?
Well, as I mentioned, I just saw some information that the draft regulatory determination has gone to the Office of Management and Budget for review. Again, I can't give you details on it because honestly, I don't know the details. They haven't shared them with me either. But what it would really mean is that we would have some authority under CERCLA, commonly known as Superfund, the act that would allow us to compel responsible parties who've released PFAS to clean up. I think Susan has something to no, nothing to add? Did I fully answer the question? I'm sorry. What was it again?
They haven't protested, so.
Okay. Sorry, I don't have a lot of information, but if it goes through the process and we do have that regulatory hook, then we will be able to enforce under CERCLA and compel people to clean up and basically back up any of the state cleanup requirements that are in place.
Question for Tim. In the MDL, are the plaintiffs water board folks such as might be here, or who's representing the ratepayers at the bottom of your box? Because they have different set of damages than a water board with an activated carbon problem.
Yeah, that's right. I mean, the MDL is 100 different consolidated cases at this point, 100 or more, and there are personal injury cases, there are medical monitoring cases, there are cases brought by states. I think New York State has a case. I believe Vermont has a case in the MDL. And then there's so I'm not sure that ratepayers are directly represented in the litigation, but you know, firms like mine, we represent the public water suppliers themselves, who ostensibly represent the ratepayers.
Tim, did you say what the? Oh, I'm sorry. Go ahead. Tim, did you say what the timeline was on the MDL?
Good luck. I couldn't really tell you. It's in discovery at this point, so you know the defendants are producing documents to us, and I believe there's it's a big process, right? So it's a lot of cases, a lot of attorneys, a lot of machination. So I think as the discovery process moves forward and the common issues start being resolved and falling off, that's when you're going to start seeing cases begin to be remanded. But I would say no sooner than 4 to 5 years from now would you see the MDL end. It's going to be a long process. There's a lot to work through with these defendants.
Hi, this is Anna Reed from the Natural Resources Defense Council. I have a question for Dr. Small. Can you provide a little bit more information on plans for UCMR 5? How many PFAS will be added? Will that count towards the 30? Any plans so far?
Yeah, that's being discussed right now. You can go to the UCMR website and you'll know as much as I know about it at this point. Again, it's just being discussed. It's still kind of far off. So 2022 before we start actually compelling people to take samples. And the systems that are sampled won't necessarily be the same systems that were sampled under UCMR 3. So, it'll give a slightly different picture of the contaminant distribution. If I had to guess, I think we're going to sample for more compounds than we did previously. We know a little bit more now. And
more the PFAS, but it's limited to 30. I mean, that's in the statutory regulation, so there's no more than 30 they can do. So looking for the PFAS will come at the expense of looking for something else, and that's just the way it is.
This is Susan Allen again from Cal Mutuals, way in the back. And I just have a question on the ground as a water supplier. there are now reports of exceedances and communicating to the public. And so a concern we have is what we actually can tell the public that's constructive, and how to address this in a way that doesn't also create hysteria and a lack of access to water. But I have a specific question, and that is about people tend to turn to bottled water, and what do we know about PFAS in bottled water?
That's for you.
Yeah. Oh, goody. Well, I believe bottled water is actually under the auspices of the FDA, Food and Drug Administration. So that's a whole other, can of worms going on there. But to address your first question about how do you let people know about these compounds and deal with just their knowledge and hysteria and that type of thing, that's kind of the million-dollar question, is that, your daily choices, you make decisions. You smoke, you don't smoke. You don't wear your seatbelt, you wear your seatbelt. All these different things, they all have their own different level of risks. So, everything you do has a certain level of risk, and drinking your water is one of those. So, we certainly could get drinking water so it's completely pure of everything, but you might be paying $10 a glass for your water. Are you willing to do that? So it's kind of where we are. So.
All right, here's what I have, the email I received on the regulatory determination. So this has a little bit more information. Yesterday, the US EPA sent the proposed regulatory determination for PFOS and PFOA in drinking water to Office of Management and Budget for interagency review. This step is an important part of the EPA's extensive efforts under the PFAS action plan to help communities address perfluoroalkyl substances nationwide. The action will provide proposed determination for at least 5 contaminants listed in the 4th contaminant candidate list, including PFOA and PFOS, in compliance with Safe Drinking Water Act requirements. That's what I have.
Yeah, well, the CCL is one step before the UCMR, and the UCMR does not necessarily have to do things that are on the CCL. So the CCL is a contaminant candidate list. So that's just basically a list of analytes that the agency might be interested in for future regulation. So the current CCL has CCL 4, and I think has 108, 105 chemicals and 112 total. So the others are microbes. So then from that list, but not necessarily from that list, that's how they do the UCMR. So PFOS, I know, it's all fun. So like PFOS and PFOA have been listed on CCL since I think CCL 3 at least, maybe even CCL 2. But then, for UCMR 3, they went and did the 6, beyond PFOS and PFOA. So it's fun. Let's just say that. You have like a magic 8-ball, that type of thing, that might also let you know what's going to be on there. So
We have probably time for just one more question. So we have internet and we need to change over.
So this one is from our online audience members. This question is specifically for Tim. As much of the PFAS human exposure is from commercial products, is there any legal action regarding this area?
I guess I take the question to mean, is there actions against local point sources? I'd imagine that there are. I'm not working on any of those cases. I guess if the question is more about, is there litigation addressed at, for instance, coatings on Gore-Tex, something like that, waterproof coatings on tents or jackets or something like that. Litigation against 3M and DuPont would ostensibly capture that. The idea is that they manufactured these mother chemicals that made their way down into products and were dispersed in the environment that way. And the opportunity is you go after, the source, you go after the top level culpable parties, and you get all of the downstream impacts of their manufacturing and also their conduct in keeping their knowledge about these products under wraps.
Okay, Will, it's 2:30, it's time, so please, big thank you to our panelists. We need about, let's say, 10 minutes. So let's return at 2:40, and we'll start our next panel. Thank you.
Standing or sitting?
Pleasure. Thank you. Yours as well.
That I did.
done, because it'll be up with the recording. Yeah.
Yeah. Okay, and it's regarding Fridays with Susan.
Yeah.
I sent you, I was not 100% sure if you got the invitation for.
We did.
Okay.
We did. We're good.
Okay.
So we'll be up in your room, 1710, during the time slots.
Okay. How much people from the?
Oh, it's probably only about 5 people.
Oh, okay.
We're
Okay.
small.
Well, I really want to be prepared with chairs, extra chairs.
Yeah, we'll be good. We'll be good. Thank you. Okay, we're going to get started here in a minute, please. Minute or two. Thank you. Tim, thank you.
My train back. It was my
I saw that, Anna.
Steve Persano, American Chemistry Council. Hi. Little concerned about your last speaker. I don't think you guys should be giving somebody who's suing a couple of my members. It looks like you're encouraging litigation. We would have told you that if you shared that agenda. Just if it was a water utility talking about the challenges they were facing, fine, but not solutions.
Ready, Erica?
I'm ready. All right. Yes. So we're starting with Jim, right? It goes Jim, then Kathleen, Rebecca, in order, right? Everything's in order. All right. All right. So if everybody could find their seats again, we're going to go ahead and get started with our third panel of the day. We're going to go ahead and get started here. And I'm going to go ahead and just give a couple of quick updates as people find their seats again for this last panel of the day. First of all, we had some really good questions about treatment technologies. And we want to just let you know that tomorrow morning there's going to be a panel on that's going to talk specifically about treatment. It'll be kicked off by a woman named Rula Deeb from Geosyntech, and she's going to talk about some of the emerging techniques that are out there, and should be really educational. So if you can, hopefully attend for that. And then we also got some great questions about risk communication, and we were reminded from one of our fellows out here that the ITRC is coming out with a risk communication toolbox sometime in the next few months. 2 to 3 months. And so that's going to be a really resourceful tool. The ITRC has been developing some really amazing resources for PFOS. If you want to get up to speed quickly, go to their PFOS website. They have several fact sheets, and apparently now they even have some videos that accompany the fact sheets. And so it's a lot of great material that's available, and it's free. Okay, so with that, we're going to dive into this third panel of the day, where we're talking specifically about exposure pathways and impact to human body and effects on aquatic ecosystems. We have 3 really fantastic speakers here with us. Jim Strandberg, who is with Woodard and Curran. Jim is a senior hydrogeologist and project manager with Woodard and Curran in Walnut Creek, California. He has over 30 years of environmental and groundwater resources experience in site investigation, assessment of human health and ecological risk, and remediation of soil, soil vapor, and groundwater impacted by petroleum hydrocarbons, volatile and semi-volatile organics, metals, pesticides, and/or polyfluorinated biphenyls. He is a member of Woodard and Curran's Emerging Contaminants Group and is currently managing the preliminary investigation of the PFAS impacts of soil and groundwater at the San Jose International Airport. He's a director and past president of the Groundwater Resources Association of California and chair of the Events Education and Affiliates Committee. Jim has a BS degree in geology from UC Davis and an MS degree in water resources engineering from Stanford University. Our second speaker is Kathleen Atfield. She's with the Center for Healthy Communities. Kathleen is an environmental epidemiologist and exposure assessment scientist with Biomonitoring California. She has 15 years of experience investigating a wide range of environmental and occupational exposures, including PFAS, pesticides, anesthetics, flame retardants, and various hormone disruptors. Dr. Atfield received her Doctor of Science in Environmental Health from the Harvard School of Public Health and recently completed epidemiological intelligence service training with the Centers for Disease and Control and Prevention. And finally, we have Dr. Rebecca Sutton from the San Francisco Estuary Institute. Dr. Sutton is a senior scientist with the San Francisco Estuary Institute and the Regional Monitoring Program for Water Quality in San Francisco Bay. She leads a team of scientists investigating microplastics and other contaminants of emerging concern in the San Francisco Bay and other regions of California. Dr. Sutton received her BS in Environmental Resources Science from the University of California, Davis, and her PhD in Environmental Chemistry from the University of California, Berkeley. She has been appointed to a California's Green Ribbon Science Panel to aid in the implementation of the state's Safer Consumer Products Regulation. And with that, we'll get started here with Jim Strandberg.
Well, good afternoon, and thank you, Erica. I'm happy to be kicking off the last panel of the day, and with that, there's some good news. Some of the content that I have has been touched on by previous speakers, so if it flew over the first time, it might hit squarely the second time, but I should be able to go through this fairly quickly. So let's see if I figure out the buttons. Alrighty. Let's see, this just provides an overview of the primary exposure pathways, and beginning with the source, through these other mechanisms, release and transport, exposure point, and then the routes of exposure. So these exposure routes I'll focus on primarily in the presentation. But what's important to remember is that in order for a receptor to actually be impacted, the pathway has to be complete. And so that's just something to keep in mind. So the pathway then is really the link between the source and the receptor. And the exposure route is the means by which an organism is impacted. And so examples here are ingestion, inhalation, and dermal. So we've seen this before, maybe even this slide. So these are just the primary or the major sources that are currently thought to be PFAS sources in the environment. And I just want to acknowledge that in this talk, I'm not going to talk about occupational exposures. Those, however, may be quite significant for workers who are routinely use or encounter PFAS in their daily jobs. This graph represents the PFAS, well, actually 4 different PFAS compounds in the blood, which about 95% of us have. So that it might be challenging to see the time frame, but it runs from 2000 to 2014. And so you can see the significant drop-off that's been mentioned earlier due to the phase-out in the 1990s. So that's great news. But there's a very real question about the replacements for some of these chemicals. So this slide is from the State Board's statewide PFAS investigation website, and it shows the landfills, airports, chrome plating facilities. So we've talked about that a little bit this morning. And it's important just to recognize that these are potential sources of contamination. Some may very well be, some perhaps not. But there's also a number of other potential sources other than just these starter industries that are being looked at right now. And that might include not only, well, not necessarily PFAS production, but more of its use in, say, clothing and textiles and in other industries. So as we know, the PFAS are mobile and persistent. The persistence we heard this morning is due to the chlorine-fluorine bond, how strong that bond is. The mobility is enhanced by its physical chemical properties, and it's very mobile in both air and in water. But these represent the primary media in which the PFAS that we're concerned about today we will cover. And so these are the primary media that we are exposed to where we might be impacted by PFAS. So these would lead to the completion of the transport pathway. And so the primary ones here are water and diet, and to a lesser extent, consumer products. And these are the media that we anticipate having the highest, where we get the most of our exposures to the general public, as opposed to occupational exposures. So, in terms of sources to air as well as exposure routes, there may be direct emissions to outdoor air. There's also fugitive dust from impacted soil. For indoor air, there's several exposure pathways, one being the inhalation of sprays in household products, off-gassing of some volatile and semi-volatile or PFAS, but that is not that common. And also the inhalation and ingestion of interior dust or particulate matter. So these inhalation sources, however, in the overall scheme are thought to be relatively low, but again, could be quite high in occupational settings. So for soil and sediment, impacts may be from air emissions or direct releases, of course, to soil, direct discharges to waterways, groundwater seepage. But the exposure routes here are also thought to be fairly minor. It includes incidental ingestion, where the photograph here shows a child with pretty muddy hands. So if the soil were impacted, the hand-to-mouth contact could be important. Dermal contact is another route of exposure, but again, it has a low potential for absorption. And then again, the inhalation and ingestion of dust particulates that we saw in the previous slide. So for water exposure routes, it could be the intentional ingestion of, say, an impacted drinking water supply. It could be an incidental ingestion. It might be swimming, showering. Also dermal contact, say from swimming, but that's thought to be fairly minor compared to ingestion. And then inhalation is not thought to be a very likely pathway because of the generally low volatility of PFAS. And so drinking water is the primary source of exposure for most of us. Also, though, the contaminated water may also impact the food supply through irrigation of crops, the water supply for livestock, and we'll talk about bioaccumulation in surface water. And it's the higher trophic organisms that are going to be more problematic for us. It's not necessarily the microscopic organisms in the environment, but it's just the accumulation up the food chain, and for instance in fish, that might be more of a concern to us. Oops. So we talked a little about wastewater, recycled water, and biosolids. And so the PFAS, may be in the wastewater discharge and may pass through and be released. Also retained in biosolids. Sometimes the precursors may actually degrade to form PFOS, for instance. But biosolids from wastewater treatment plants applied to land, though, that does save incineration and land filling. So again, it's maybe a societal trade-off. And the biosolids reuse in many industries, in agriculture, as fertilizer, landfill cover. So it's, as it was said before, ubiquitous. PFAS in the diet, and here we talk again about the bioaccumulative properties, so it could be fish and moving on up the food chain from there. But it is it's highly variable by compound and by the type of organism. But the uptake could be through the water. It could be into fish and wildlife, and PFOS, the C8 longer chain constituent is the main PFAS that's detected in fish and wildlife because they tend to bind to proteins, whereas something like, say, PCBs, which we're perhaps a little more familiar with, they tend to bind to fats. So PFOS tends to bind to proteins. In produce, smaller chain are taken up more so than long chain. And lastly, the transfer of PFAS from packaging just directly into our food. So we look forward to some improvements perhaps in that area. Then in commercial products, I think Erica had a slide this morning that showed just the vast number of different products that that either have or still contain PFAS constituents. And even though the U.S. phased out PFOS and PFOA in the 90s, the ban did not extend to other countries. So as we import products from around the world, they very well may contain these chemicals that we've tried to remove from our own manufacturing processes. And so while the PFOS and the PFOA are phased out, there are new PFAS compounds that are becoming of higher concern. That would include PFBS, and then some of the PFAS precursors like Gen X and Donna. So the net effect, though, is that there's probably a relatively small contribution from our diet, but in some cases, you know, the concentrations or the contributions from diet could be quite high. So infants and toddlers, we heard earlier that there is a transfer of PFAS from mothers to babies, and that younger children generally have a higher rate of exposure. And that's also due to their lower body rate and body weight. So it's relative to that. And that would include, you know, crawl around on the carpet and a lot of hand-to-mouth contact. So the photo shows a baby with nearly the whole fist in the mouth. But, you know, with carpets and dust, it seems that that would create a higher exposure for toddlers. So in summary, there are you know, numerous sources of PFAS in the environment. The exposure pathways and routes, number one is where drinking water is impacted. That's likely the main source of our exposure. Otherwise, diet, home dust, commercial product use present the next highest exposures. And we just mentioned that it's higher for infants and young children, higher for those individuals living in areas that are impacted with PFAS, perhaps from atmospheric deposition or direct application to soil or water, and of course, employees who work with PFAS directly. And we also were glad to see the significant decrease in blood levels in the U.S. population, but that may also be a factor of what we're looking for. And with that, there'll be further work, I'm sure, on some of the replacement compounds. So that is it. Thank you very much.
That's for you.
Good afternoon. I'm Kathleen Apfield. I'm from the California Department of Public Health, and I'm here today to talk to you about Biomonitoring California's projects where we've been looking at PFAS in serum across California for about the last decade. So just to introduce the Biomonitoring California program to you, if you're not familiar with us, we're actually a multi-agency program across the California Department of Public Health and Cal EPA, specifically OEHA, and Department of Toxic Substances Control. And we were founded by legislation in 2006 to look at determining biological levels of environmental chemicals in Californians, to look at trends across the state, across time, across various different types of demographic groups in California, and to use this information to assess the effectiveness of our public health programs and our regulatory programs to hopefully decrease exposures to specific chemicals. Now, since 2010, we've had various studies that have looked at PFAS in different groups across California. So you can see with the arrows, different sort of areas in California, and then different types of groups. So we have general population, study with Kaiser members in 2011 to 2013 in the Central Valley. We've also looked in pregnant women, in Asian Americans, in firefighters, and more recently, we're going back to a more surveillance approach across different regions of California, starting in LA County. And just a little more details if we need them. So I first want to caution everyone that comparing studies is really tricky for PFAS for many of the reasons already been elucidated by our earlier speakers. It really depends who's in that particular population that you have picked to survey at that moment in time. There can be big differences by the proportions of the sexes in your study group, as well as their ages, and of course there are significant time trends that we are now seeing. So here's an expanded version of the same graphic that Jim put up for us. So the CDC, of course, does their own nationwide sampling of various environmental chemicals in 2-year cycles. It's the National Health and Nutrition Examination Survey. So from left to right, we have PFOS, and that has decreased about 80% from 1999 to 2014, then PFOA, PFHXS, and PFNA. So all of these seeing decreases when you're looking at general population levels over time. So for California, again, as I said, it's really tricky to compare studies directly. Where it's easiest for us is where we have looked at banked maternal bloods in our genetic screening program here in California. So on the left-hand side, the green dots are from 2000 to 2003 samples, and the navy are from 2012 samples. So we're seeing decreases, PFOA, most dramatically for PFOS, methyl PFOSA, PFHXS, and then the PFNA is actually looking like it was holding steady amongst the women between these two groups. So for the rest of the talk, I want to focus on 2 studies more recently occurring. One which is a targeted study, we call sort of targeted and then general population studies, but this is a targeted study called ACE among Asian and Pacific Islander communities, so looking at their exposures. This was built off of a community-based study that our branch, I'm in the Environmental Health Investigations branch at CDPH, was doing with various groups on safe fish consumption. Now, of course, this was originally more focused around metals such as mercury. But based on the study in the Central Valley, we had seen the Asian subpopulations there have higher levels of PFASs. So this gave us an opportunity to maybe drill down a little more and see what could be related to those higher levels being seen there. So we did 32 PFASs there. I only have time to present a subgroup of those today, but feel free to ask me more. We did 2 cycles, one in San Francisco among Chinese Americans and one in 2017 among Vietnamese Americans in the San Jose area. And the groups that we recruited ended up being about half male, half female, average age of 46. Income was below the region's median income, and importantly, a lot of them were actually immigrants, as will play out in a moment. So when we look at the concentrations in their serum, I'm going to focus on the 5 most prevalent. So these are the ones that are at greater than 98% prevalence being detected in the serum. So PFOA, PFOS, PFHXS, PFUDA, and PFNA. And the levels for PFOS is, of course, the highest at 7, and the others around 1. And to compare it to NHANES, I'll give us a graph for a visual. And again, a slight caution in that this is using NHANES data from 2015, 2016, so it's pretty close, but it is a little earlier. So you might expect those numbers to be a little lower still if we were to have exactly contemporaneous data. So the first two bars of each section are one, the East 1, the San Francisco group, and East 2, the Vietnamese Americans of San Jose. And to draw your attention to the box, I am comparing to the Asians within NHANES, and the boxes indicate where Asians and NHANES tend to be greater than general population anyway. So if we focus on those for PFOS, ours are a bit higher than the Asians in NHANES, and PFNA, a little bit higher. And then for the others, pretty much comparable, perhaps a little bit greater for PFUDA. To dig into a bit of the demographic trends, adjusting for other, each of these adjusting for other demographic factors. So we do see a very predominant role of sex in that males were 1.8 to 4.6 times higher than females for PFOA, PFHXS, and PFNA. PFOS in some studies is seen also to have that sex difference, but it didn't play out in this group. There's a strong age-sex interaction that we see. So generally, the increase in age is seen more prominently in women for PFOA, PFHXS, and PFNA. PFOS seem to increase equally with age. And again, because this group was predominantly an immigrant population, we wanted to look at some of the acculturation factors or immigration factors that might play a role. We have to think about sort of body burdens people may bring with them or particular cultural practices. Just sort of some of the higher level, more proxy kind of factors such as birth country and the interview language. Here, non-English, we saw those actually increased with PFOS, PFHXS, and PFUDA, sometimes rather distinctly. And the greater portion of your life spent in the United States seemed to be almost protective. You had lower levels with PFHXS, PFUDA, and PFNA. And you can see the numbers if we want them later. So I did want to compare that to some of the international studies. We do, of course, talk a lot about the various concentrations within the United States, but PFOS and PFOA are still being manufactured or maybe just were shifted to China and other countries in the world. And so there are areas where there is sizable contamination present. And of course, China is a very large country, so biomonitoring efforts there give you a wide range of results. Some comparable to the United States and some that are much larger. So distressingly, an example being employees of a contaminated fishery where the median PFOS levels were at 10,400 micrograms per liter, and residents near a fluorochemical industrial park of PFOA at a median level of 9.4 micrograms per liter. There are no PFAS biomonitoring studies that are yet reported in Vietnam, so I cannot compare it there for you. To move on to our California Regional Exposure Study, we are now sort of marching through the state. We've divided it up into 8 regions for logistical and resource concerns. And this is more a general population look over time. Recruiting 300 to 500 participants per region. We're focusing on metals again and PFASs primarily, but where resources and local interest is indicated, we can add other pollutant panels. Our first region was last year in LA County. In the spring, we recruited 430 people, and 12 PFASs were measured there. So again, those 5 that I talked to you about for ACE, those are still quite prevalent, and over 97% for 4 of them, PFUDA has dropped a bit down to 82% detection. That methyl PFOS kind of sticks out at the top there. Partly it's so highly detected there as the detection limit is quite low for that compound. And again, I am afraid I have to compare to more historical NHANES data. So the fact that our levels are 33% to 55% lower than those national values may be more an indicator of the temporal trends than that California is necessarily very different. But it'll take us a bit to tease that out as we learn more from our questionnaire data and as the next round of NHANES comes out. So as has been alluded to, it's very common, of course, to have any PFASs in your blood. At least one was found in every participant, an average of 7. Again, we saw a sex difference for now 4 of those compounds: PFHXS, PFNA, PFOA, PFOS, and again, an increase with age. We saw, again, our trend with Asian participants having higher levels, especially of PFOS, 200%. PFNA and PFDEA. Of note, these levels were actually lower, their levels, so that the Asians in KRLA were lower than the ACE ones that I was just reviewing. We also saw relationships with higher education, especially for PFOA and PFUDA. I want to draw attention to the fact that our levels do not, for the KRLA surveillance, show immediate evidence of highly impacted individuals. So let's see how legible this is. The horizontal bars at the top are our occupationally exposed workers, and these are average blood levels, and the vertical indicators are on the log scale, so keep that in mind. And marching down are exposed communities, and then NHANES down at the bottom. And so I've drawn in a bar with an arrow down showing you basically where our 95 percentile is. So our 95, our most extreme individuals are really not getting anywhere near the average levels of any particular exposed community in the United States so far. So that's just sort of initial indicators of this one region of California. So now teasing out the various contributors to these levels. Now, of course, living in an area that has contaminated drinking water is going to have a huge impact. It could be up to 75% of your levels. And we've seen interventions play a part in lowering people's levels. It's a graph from Minnesota after the installation of water filtration systems there. Of course, highly contaminated foods, such as the contaminated fishery in China, and then our other large contributors that we know of are sort of sex differences, which are now, we don't really understand those very well, but we do think contributions are from menstruation and from pregnancy, breastfeeding, and of course, age, how long you've been around to be exposed to these PFAS. We have extensive questionnaires for ACE1 and ACE2, especially for very culturally specific items and consumption patterns of fish, various types of fish and rice cookers, that we'll be looking into more personal care products, cleaning products, and for KRLA, specific foods and hobbies and occupational types of exposures. So we do see some initial associations with, say, fish and with some rice and food packaging, but this will bear out with further examination. Moving into the future, or the present, really, this spring we were in eastern and southeastern California gathering samples from 359 participants, so those are now at the lab being analyzed. And next spring we will be in San Diego and Orange County. And with that, I'd like to say thank you so much to all the participants, everyone who's willing to give samples and their time to the state. And thank you to our staff and funding and all the various community groups that help us put this type of work together.
All right. Great to be in front of everyone today. My job today is to shift us a little bit away from the human health focus and think about the toxic impacts that could be occurring to our aquatic life here in the state. So I'm actually not a toxicologist, I'm an environmental chemist, but luckily I got a lot of help putting these slides together from an actual environmental toxicologist, Dr. Liz Miller. And Liz and I work at San Francisco Estuary Institute, which is a small research institute in the San Francisco Bay Area, where we do a lot of water quality and ecology research focusing on California's wildlife, trying to keep us healthy. After all, we've got some states setting fish tissue guidance, and they're putting up these signs in certain areas saying, hey, people, don't eat these fish because they got PFAS in them. But what about the wildlife eating these fish? Are they facing some risks as well? And we know these compounds are not just in people and not just in fish. Here's a figure from a recent marine mammal review showing perfluorooctane sulfonate, the C8 sulfonate, in all kinds of marine mammals all over the world. So these chemicals, as we would expect, are really widespread in our wildlife. So what can we say in terms of what's in aquatic organisms? What's accumulating in tissues? Generally, we can say that C8 sulfonate is one of the more widely and highly observed compounds among the larger PFAS class. So here's one little chart from a recent study showing 3 different marine mammal species in this case, and the diagonal lines are the PFOS, the C8 sulfonate. And you can also see from this that there's differences in the distribution of the different PFAS compounds by species, and in some cases that's due to differences in metabolism and excretion. We know that these things like to hang out with the proteins, right? They're not lipophilic, they want to be with proteins, so we end up seeing them in the blood, the brain, the liver, and other organs. That's where we want to look for them. And we also know of maternal transfer to offspring, so this is one way these chemicals are passing around through the larger population. Okay, so these compounds are in our animals, our wildlife. Are they toxic? Well, just some overarching comments. Most of the studies we have, it's a pretty limited data set, right? But I'm gonna give you some highlights. But most of the studies we have are on PFOS and PFOA, the C8s. But we do know so far that effects do seem to vary with chain length, with that functional group, like the sulfonate versus the carboxylate, and with species and sex. We see diverse modes of action, just like with people, so these compounds are having different impacts on the organism, and that means a lot of different endpoints we need to look at when we're looking at toxicity studies. And I'm gonna focus on 2 particularly sensitive classes of organisms and just give you, again, some highlights. Birds, aquatic feeding birds, and marine mammals. Okay, so birds. What can we say about birds? We got birds in our state eating a lot of our fish. Is this safe for them? Well, we can look up north to Canada, where they've actually got some guidelines where it's like a fish tissue guidance, but for animals instead of people, where they've come up with these federal environmental quality guidelines for wildlife diet. So what they say is, if you want healthy bird populations, ideally, these birds are eating prey fish, which generally are smaller than what we eat. The prey fish at 8.2 nanograms per gram wet weight in the whole body content. So we have studies in San Francisco Bay on some of these prey fish that our birds eat. And unfortunately in our bay, we're seeing levels up to 240 nanograms per gram. So compared to this Canadian standard, we would say, our birds might be eating a little too much PFOS in their diet. What are the kinds of impacts we're concerned about with birds? Well, a lot of our studies, our best studies, are on developmental toxicity, where we're basically trying to answer the question, do healthy birds, baby birds, hatch from the eggs? And so 3M sponsored a study a number of years ago, and what they ended up coming up with was what's called a PNEC, or a predicted no effect concentration. This is meant to be a protective threshold of 1,000 nanograms per milliliter in the yolk of an egg. And so they're saying this would protect against developmental toxicity. Now, there's actually been a field study of tree swallows in the Great Lakes area that actually found reduced hatching at much, much lower levels, 150 nanograms per gram. However, just last month, this same research group went out and looked at a different tree swallow population and didn't see effects that low. So there's now some question as to whether developmental toxicity might be happening at that low level, or maybe there's some other contaminants involved. Now, going back to Canada, Canada's come up with a guideline in terms specifically of the bird eggs, and this is again for the C8 sulfonate, suggesting we want eggs 1,900 nanogram per gram wet weight or lower. So that's what they're thinking in terms of a safer bird population. So what do we have in California? Well, we, at the San Francisco Estuary Institute, we work with San Francisco Bay's regional monitoring program, so we've been conducting cormorant egg studies over the years, regular monitoring of PFOS and some of the long-chain carboxylates. And so we've got this nice data set, and we can lay over these different guidelines or toxicity thresholds and see where we're at. So what we're seeing here is that the levels in our cormorant eggs, and this is the southern part of San Francisco Bay where we tend to see higher levels of a lot of contaminants. The levels are in the range of these various thresholds or guidelines. It kind of depends on where the sort of data is going to land as we do more studies, just how concerned we need to be. But I should note that these guidelines are specific to one single endpoint, developmental toxicity. There have been a few other more recent studies showing a lot of other endpoints, mostly non-lethal endpoints, so we don't know how these might have any impacts on the wildlife, but we want to keep in mind those diverse modes of action, so we can't just look at one endpoint exclusively and assume we've got our species protected. Now, one good point about this nice status and trends chart is we are seeing those declines, which we've seen in people too, right? So we think that's the phase out. So regardless of the risk our birds might be suffering, hopefully that risk is going to be declining thanks to the phase out. Okay, so that's the C8 sulfonate. How about PFOA and the carboxylates? So we've got some studies here, fewer studies on our birds, unfortunately, but they do suggest, oh, these compounds could have similar effects to the sulfonate, maybe at similar levels. Do we need to be concerned about PFOA? Well, again, going to our South Bay cormorant eggs, luckily for us, PFOA is generally at a lot lower levels in your aquatic animals. So if you look just at developmental toxicity and what we know right now, again, few studies, maybe we don't need to be concerned so much. But of course, it's never that simple with this class of compounds, right? So there's been a few studies now on wild populations suggesting that some of the other long-chain carboxylates are linked to reduced hatching. And this is out in the wild, seeing correlations of higher body burden with reduced hatching. And we don't know for sure whether this might be a problem with the embryo or a problem with the parental incubation behavior, perhaps hormonally mediated, but there seems to be some kind of effect here. And a couple of different wild species, we're seeing linkages to protein damage. So remember, these guys like to hang out with the proteins. They might also be damaging the proteins. We don't know if that's going to have an impact to the population, but it's certainly concerning to see current levels associated with a health impact, a change in the health of these species. So how about California? These aren't California populations, right? When you look at again, are going to go back to our cormorant eggs, you see a number of these contaminants in our cormorant eggs. Now these levels, they're lower than the PFOS, the sulfonate, right? But they're still in the same range, unfortunately, as some of those wild bird populations where we're seeing impacts. And the other thing we're seeing is not really a sense of a clear decline like we do with the sulfonate, the PFOS. So the phase out isn't being as effective here in reducing our wildlife burden of these types of compounds. All right, so that was birds. Let's talk about our marine mammals. We got a lot of those in San Francisco Bay and all over our coastal waters, right? These are also more sensitive species. So again, I'm gonna look to Canada and I'm gonna look at those guidelines they've developed to protect wildlife species, where their guidelines are more for terrestrial or semi-aquatic animals, or mammals rather, but what they're saying is you wanna be eating fish that are 4.6 nanogram per gram or less if you want a healthy marine mammal. So remember, in San Francisco Bay, we've got the small fish that are up to 240 nanogram per gram, and then the larger sport fish, like the ones we eat, are up to 17 nanogram per gram. So again, this is exceeding that more protective threshold out of Canada. So that does suggest our marine mammals might be eating too much of the perfluorooctane sulfonate. The types of impacts we're most concerned about with marine mammals, well, one of these is immune system health. So these can be immunotoxicants, and there's a really interesting study out of South Carolina looking at this pretty heavily impacted bottlenose dolphin population, where they saw higher levels of a bunch of different PFAS linked to a whole host of different immune activities and assays, and the overall conclusion of this study is the more highly exposed dolphins were actually in the state of chronic immune activation and were likely more susceptible to disease. And it's interesting, we actually saw a little hint of this a number of years ago in a study in Southern California looking at sea otters that had beached themselves, where we saw sea otters that had higher levels of PFOS or PFOA in this study being more likely to be diseased. So this is, again, a connection to our state's marine mammals and their health. One of the other concerns we have is the liver. So these guys concentrate in the liver, and one of the things we see in lab studies when you take liver samples from marine mammals is that PFOA and some of these long-chain carboxylates can cause activation of PPAR-alpha, which is the peroxisome proliferator activated receptor, and that's concentrated in the liver and a few other organs. And the problem with this activation, especially for marine mammals, is that it's going to disrupt your lipid and carbohydrate metabolism. So the marine mammals, they've got the blubber, they need that to survive, so you really don't want to disrupt their lipid metabolism. So this one group, Ishibashi et al., they actually didn't just do lab studies of, in this case, baikal seal livers, but they also went out to a wild population, and they saw signs of this activation out in the wild baikal seal population in Russia. So again, this is connecting current levels of exposure to potential concerns in our wildlife. And we've done studies on our harbor seals on levels in serum. We haven't looked at their liver. We haven't looked to see whether activation is occurring, but we do see similar levels as these baikal seals. So that's another indication that we want to think about our marine mammal health with these exposures. I also want to talk about uncertainties. This was a really interesting study of a whole bunch of different marine mammal tissues where this group used a variety of different techniques to come up with a total fluorine mass balance, all the different fluorinated compounds in these marine mammals. And while they did end up finding that the C8 sulfonate, the one we know about, was the dominant substance, they also found a whole bunch of other PFAS. So they were looking for a total of 36, and they found a bunch of those, but they also think they've identified 33 others that no one's really looking for and that maybe we should be looking for in our marine mammal populations. And so these new contaminants, we don't know their toxicity, and we also don't know what their impacts might be in these mixtures that are currently being, where the animal's currently exposed. So this is a pretty big deal, mixture toxicity and the larger burden of this larger class of compounds. All right, I'm going to take one quick foray and then go to my conclusions. This quick foray is away from animals to our plant friends. Because, we focus a lot on animals, we're animals, but unfortunately, these compounds can have some unique impacts to plants. And this was a pretty interesting study I just read on some of these alternatives like GenX, where this lab exposed a marine microalgae to a few of these different alternatives. And they ended up finding growth inhibition at levels as low as 10 nanogram per liter, or 10 part per trillion for 2 of these compounds. So that's a pretty big deal. That's a really low level to be causing growth inhibition. So we just want to keep our plants in mind and not just exclusively look at animals when we're thinking about ecotoxicity. All right, my last slide, my take-home messages would be PFAS are widespread in biota, just like in us. Diverse modes of action, just like in humans. So we got to be thinking about a lot of different endpoints when we're thinking about toxicity. We're particularly concerned about the C8 sulfonate, the high levels compared to what we know about toxic effects. though luckily the levels are declining thanks to the phase out. We do still have concerns about other PFAS, including the long-chain carboxylates, even at current levels of exposure. And then we got a lot of uncertainties. We really lack toxicity data in this realm for animals, for plants, and in particular, we're very interested in mixture effects because we're all exposed to these in mixtures. Thanks.
Okay, so we're gonna start the question session, and while we get microphones out to the people with questions, I did get a text message from my friend Simona Balan, who will be giving a talk tomorrow on, she's from DTSC's Safer Consumer Products team. She told me that the chocolate cake that I mentioned earlier, FDA determined that it might have been a false positive. So just so you guys all know, the chocolate cake may have not had that much PFOS in it, but other things probably do. Okay.
Thank you. My name's Adam Love. I'm with RU, an environmental consulting company. I was hoping the speakers could clarify some of the information that was presented in the panel. There seemed to be the statement that said that drinking water was the primary human exposure, yet the dynamics that you see in the change in PFAS calculation in blood don't necessarily reflect that. And so I was hoping that the panel could clarify this issue of, is drinking water the primary exposure, or is it not? Because the change in blood levels don't reflect changes in concentrations in drinking water, for sure.
Let me clarify a little bit of what I meant. I guess what I meant to say is where you have a very contaminated community, that is definitely going to be the predominant driver of your serum levels.
What concentration?
Oh, well, I mean, we don't.
You can't say that if you don't know what the concentration is.
Well, we're comparing quite, I don't have the numbers off the top of my head, and I don't know that there is any kind of bright line for that, but, these are very different concentrations in contaminated communities versus sort of the general population drinking water. As far as general population levels, we're all still trying to tease those out, and I think they can vary from group to group as far as what are going to be the predominant contributors.
Excuse me, Greg Kester again with CASA. And just a point of clarification, Kathleen and Rebecca, to all of the data that you exhibited were in the parts per billion range, correct? They were all micrograms per liter versus what we were talking about this morning in the OEHA risk levels of 0.1 part per trillion. So I'm just wondering how those compare. I mean, if our blood levels are already in the multiple parts per billion, then a level that low is really never going to be felt in our bloodstream.
All right, I can address that question. So part per trillion exposures, so parts per trillion levels in the water lead to parts per billion levels in the serum. So it's because of that biocumulative properties of PFAS. So it's kind of looking at apples and oranges in this case, the water versus what's in the serum. I don't know if that's helpful or not, but.
Hi, I'm Teresa Slivko, Metropolitan Water District. I'm curious if you have some data that can show us a comparison of the concentrations in other routes of exposure. So, for example, in dental floss and how much you're getting from the dental floss, or food wrappers, pizza boxes and so forth, popcorn and things like that, just so we could see a comparison of what it is that we're being exposed to by these other routes.
Well, the problem is we can't quite experiment on humans too much, and there haven't been those sometimes there are voluntary studies of sort of replacing people's products, right, with one thing versus another to be able to look at the decreases. So I don't think at this point in time we can really try to say what portion is from any one of these particular consumer products. But some of them have been seen. So the Glide floss has been seen in a study. There's also, microwave popcorn has been seen in some studies. But as far as being able to tease it out to a source contribution yet, I don't think the data's clean enough to be able to do that for you. We will be working on it, and I'm sure others are working on it.
And while they're transitioning, I just wanted to put another plug in for one of the presentations tomorrow by DTSC, who are doing some work on their efforts to address PFAS as a class through the Safer Consumer Product process.
Luisa Zainez from Valley Water. I was just curious if some of the levels you're looking in blood, are you starting to look at the shorter chain Gen X? You said you look for 32 or 12 compounds. How many of those were the replacement compounds?
I can bring up, I have an extra slide of those two.
On this slide deck.
Yeah. Right. Let's see if I can spot which it is first.
I can ask my question while you're doing that. This is Jake Madden with San Mateo County LOP. Has there been any study looking at sampling material? I know like Teflon tubing is commonly used for low purge flow, VOAs with, little Teflon septums, that type of thing. Is there sensitivity towards that?
Oh, I'm just.
So to go back to
I can address. Oh, why don't you go ahead?
there has been some testing done by some of the manufacturers. QED comes to mind first. And they're not finding a lot of PFAS, or sometimes any, coming off of water, PFAS-free laboratory-provided water coming through the Teflon tubing. And the thought is that the contact time is so extremely short that it's not as much of a concern as it initially would seem to be.
So I have two slides here of the additional ones other than those 5 that I had talked about earlier. So obviously this is not all the 32, and I don't have listed out everything else was sort of non-detect for both the ACE1 and ACE2. So sorry, I don't have the full list of those. These are available, I believe, on our website, so you can see the longer list there. So yeah, in ACE we did do 32, and in CARE we're only doing 12 at the moment because it's a faster process. The 32 is not fully automated, and we have to work under various timeframes to get results back to our participants. So are there any of these that were a particular note? I'm not sure where the question or what was. We've got PFBA and PFBS here. PFBS is pretty low, PFBA is reasonably high.
I can make one small comment where I think the short chains might be more readily excreted in the urine, so that might be where you would want to look for short chains. I think I saw a study
we don't
on
have a
CDC.
urine method. I know the CDC started making a urine method, but they've actually decided not to go forward with it, actually, for some, yeah.
Kathleen, my name is Lynn Love. I'm with SCS Engineers. I understand with your CARE program, you're going to be looking at communities in Orange County. Are you going to be focusing in on the Santa Ana, Orange, City of Orange areas in order to see if there is some sort of correlation between the contamination in the drinking water wells and the population?
So the care studies are set up to be surveillance. So they are we do have sort of distribution requirements, geographically, sex, race. So those are not designed to target specific communities. I do know that the CDC, the ATSDR study that is supposed to be launching, has chosen one of its sites to be outside Irvine and Yorba Linda, Orange, and what was the third?
Tustin, Santa Ana area.
Is it that, okay, that third community there? So they'll be focusing on that area and comparing to Massachusetts, Colorado, Michigan, and a few other sites that have been chosen. So that may be a more targeted look that they are able to do.
Great, thank you.
Mm-hmm.
So this is Andrea Ventura with Clean Water Action, and Dr. Sutton, you may have answered my question, but I had a comment and a question. One is in terms of the exposure routes, products versus water versus food. One of the concerns that some of us have had is that the products end up in the waste stream that contaminates, our water or other environmental media. So that would, it's a cycle that will come back to haunt us. But my question, you may have answered it already, was when you're looking at either other animals or humans, for short-chain, is blood going to be the place to look? And you mentioned urine, but I'm also curious about the body's organs and anything else that we don't know about.
I don't know about other organs. I saw the one CDC study suggesting that urine might be where you would want to go for the short chains. But if they're shelving the method development, that might get tricky.
Right, and currently our program only looks at urine and serum. Of course, not other organs, but not hair or nails or other, or fecal matter, I suppose.
I'm Rob Schofield from GSI Environmental. I have a question for Dr. Hatfield. Did you compare any of your serum levels to exposure limits, or serum levels corresponding to NOELs? Like, do you have a guideline to compare, a safety level to compare it to?
No, there's not really one that's sort of equivalent for serum levels. And we haven't tried to do any sort of back extraction to estimate what sort of the input exposure would have been. It's very tricky because, of course, these are, they bioaccumulate, they've been in our body for a long time, so it's hard to know how much of this is a recent exposure versus how long it's been carried in the body. So it's tricky.
Just a question and a comment. Dr. Ravi Naidu did what you'd call an anecdotal study of his group, and they tested their group for PFAS in blood, and found one of their researchers had elevated levels. And when they questioned him about it, it related back to the fact that he fried himself an egg every morning with an old Teflon pan. That's anecdotal. I guess the question is, how much do we know about that, the persistence of these old pans and things like that in terms of being a route of exposure for people?
I don't know the answer to that question very well yet. I think people are still looking into the transfer properties of various food packaging materials into the foods that we eat.
This is for Jim. This is kind of getting back to that question about use of sampling materials that have Teflon in them, and the fact that we don't see contamination because of this short contact time. And I think that is true. That's what studies done by USGS scientists have found. I think I also read something that the PTFE, the Teflon that we usually use, is, okay, I don't know the chemistry on this. It was something about the repeating units, the CFs that had an oxygen on them or something, were usually very short chain. So if they broke apart, you wouldn't get our target analytes.
Yeah.
For example, we only start at the PFBS, PFBA, the 4 carbons. So there may be PFAS that are shorter chain than that are coming off of it.
You know, in answering that question, what I could have said was that the orders that I'm familiar with at the state board, regional board have issued for airports, for example, I mean, the guidelines from the state board tell you not to use those kinds of products, and so we don't. What I had relayed earlier was some information, and there are a couple of published studies about others, you know, manufacturers who are testing their own products to see whether or not they really do emit the PFAS constituents. In the meantime, though, they've already converted and they're already now using other materials. But in some cases, those are very limited. So high-density polyethylene is being used in some cases instead of low-density, yet it's a much more brittle and difficult-to-use material. So in cold regions, it's more likely to crack. And so they're using it because it's suggested or directed not to use the low-density polyethylene. But I think there will be more studies that come out. And so that was, and I don't know if that's being done under any regulatory auspices or if these are just individual manufacturers who have taken it upon themselves to do these studies.
Right. Well, again, we try to stay away from those, and we've even done some topical quality control samples to see if they could be contributing. And there's a real concern with the Teflon tape that they've seen. But actually, if that happens if you soak, you'll soak Teflon tape for a period of time, like hours or days, and then you'll get just enormous hits. But if you're using a little Teflon tape to seal up a fitting or something, and again, the low contact time, we are not seeing that having an effect on our samples.
So I would just add that, you know, one of the things that a lot of folks are doing is just changing gloves very, very frequently. So you can't necessarily wear a safety vest even though you're in the street because it's been treated. You're not supposed to wear leather boots because the leather's been treated. So there's a very long list of do's and don'ts, or more don'ts. And I think what time will tell is how practical those really are. And if you can you or can you not use Ziploc baggies? You know, I think you can, but you know, we don't use other things as well. So it's I think the science will mature, the industry will mature as we all just learn a little bit more.
We have 4 questions from our web viewers.
This first question is from Melissa Nelson. She's a registered geologist at the Santa Barbara County Public Works. And her question is this: regarding the preliminary ecological risk talk, what is the correlation between concentration in eggs, birds, and algae versus the concentration in water? In other words, some concentrations were thrown out as suspected to be unsafe in animal protein, but how does that correlate with levels in the water?
What we generally see for fish is that levels are correlated with what's in the sediment, not what's in the water. So fish, what we think is that they're eating like benthic invertebrates, and that may be the pathway of exposure. So the water is not necessarily going to tell you how exposed the fish are, and therefore how exposed the greater food web is.
The second question is from Jenny Lagerkist, who is a remedial technical manager at NAVFAC SW. Her question is, can California provide a status on providing usable eco-values for risk assessments? Is there ongoing research regarding this?
The main screening levels that we're using in Region 2 are the ESLs, and our key people who work on that are Russ and Nicole Fry, Russ Steenson and Nicole Fry. It's on their radar, and they've started to do some research. The majority of the information that's out there is for human-based health screening levels and not ecological, so those are probably kind of a ways out as, additional studies kind of get compiled and toxicity data become available.
And the third question is from another online audience member, and her message is this: what studies are being done for the replacement PFAS? There seems like there could be a false sense of relief with the phase out of the longer chain compounds, especially as some producers/users are conflating the phrase out of PFOA by saying that they don't use quote unquote this material anymore, even though they are using replacement PFAS.
For the Biomonitoring California study, yes, we are still in the process of mostly looking at the sort of big 12. We do hope to expand, hopefully at least to continue those 32 as the lab becomes more automated. But yes, it's an ongoing question of how do we expand that so that we don't get a skewed view of what is occurring. So it's on our radar, but we don't have the answer yet. I don't know if others.
Does anybody have any other questions they want to ask? Okay, we got some of the mic.
I'm Usha Vedagiri with Wood, and actually I have a comment and a question. For the question about eco values, I just wanted to say that ITRC has just started a surface water quality criteria subgroup for PFAS. I'm on that subgroup, and one of the goals of that subgroup is to spend 2020 and possibly some time after that, looking into approaches for developing surface water quality criteria that would be protective of human health as well as aquatic biota. So, and Ross knows that. My question is actually a really difficult question. When New Jersey was developing their low MCLs, one of the points they made was that even at the low serum levels found in the population, that there was still a possibility that adverse effects could be happening. And with all your biomonitoring data, I'm wondering if you are also trying to link it to any epidemiological information about whether any of these very subtle effects could be correlated with what you're finding.
So far, all ours are generally cross-sectional. We don't follow up with participants to look at development of any particular outcomes. Some we may be able to look at some more historical, sort of cross-sectional again. One of our first studies was in tandem with Kaiser. So at that time, there had been an agreement to be able to look at least contemporaneous types of health indicators, but most of what we do is just cross-sectional, and we don't ask about health information. I could point you again to that the UC Irvine part of the CDC ATSDR multi-site study, which would at least give some California information. I think that community is a bit lower exposed than some of the other ones, but we do need a range, of course, to look at dose response types of situations.
I'm going to ask a question if there's not a mic out there. Is anybody holding one? I was curious, I've always wondered, with the fact that PFAS are found and bound in proteins when we do the blood serum sampling, does it account, I've heard some scientists talk about whole blood sample instead of the normal type of blood serum analysis that can be done, and I was just curious if we have that incorporated into, how that's addressed or if it's even an issue.
All of ours are, just the serum. Serum samples is all that we've looked at.
Is it possible then that we actually have kind of biased low results in terms of what is in the blood of humans?
I wouldn't say so, but I'd have to, get back to you on that to make sure I give you the right answer, I'm afraid.
Okay, well, I think with 5 minutes left, I'm going to hand it over to Wendy to close us out.
Thank you. So I just wanted a reminder, we're going to show the movie at 4:30. We'll be at the Sierra Hearing Room. We really, really appreciate all your participation and attendance today. I hope to see you all back tomorrow. Just remember the agenda. We have 2 panels in the morning, and then I hear things are hopping in the Datathon. And so they'll be in to provide their results or, what they've been doing. So after lunch. So we look forward to seeing you again. Just remember, you can drop off your badge on the way out. There's a little bucket there. And then unfortunately, you're going to have to go through the process again tomorrow morning because of security. So you'll have to go through the check-in process again. So anyway, thank you very much. Please have a safe trip home. Thank you. If you wanted to skedaddle, that's fine. Thank you very much. Could you at registration? Yeah. Okay, yeah.